It's struggling.
Okay, good morning, everyone. I think that's better now. There's no echo. I think we should start because we have to keep to the time. And I'm sorry for those who thought it was 8 o'clock. The starting time was 8:30, but of course, registration was much earlier. So thank you so much for joining us. We have a number of people who are online, and then I understand some people will come tomorrow. We have a few colleagues who've also sent apologies and so forth. So I hope that by tomorrow, maybe the numbers might increase. But my name is Sibusiso Moyo. I am the Deputy Vice Chancellor for Research, Innovation and Postgraduate Studies at Stellenbosch University. But I'm also a mathematician. And when I was busy in the department and faculty, I focused quite a bit on differential equations and their applications. And then I have interest, of course, in mathematics, mathematical physics, and then the applications as well, mainly working with engineers, people from computer science and other fields. And in here, we have a number of people who have joined us. And I want to thank all of you. And I know some of you have traveled, but some of you are from Stellenbosch. So thank you for joining. I hope we have time to do introductions later. But just I think for the sake of those online, I'll skip that part and then we can introduce ourselves later. But for now, just to say, a special welcome to the Dynamical Systems Theory and Modeling AI workshop, which takes place from today, which is the 19th to the 21st of November. And for us, it's really special because the aim of the workshop really is on dynamical systems theory and modeling, and of course, and AI at Stellenbosch University. And we aim to bring together, of course, researchers, educators, and students working on theory applications and modern computation approaches to dynamical systems. So the program, of course, which you have, will explore the synergy between classical methods such as Lie symmetries and integrable systems and contemporary techniques which involve machine learning and AI. So we have a number of colleagues here, also faculty members from Stellenbosch University, who will be able to share with us today. So through a carefully curated schedule, the workshop will emphasize the role of dynamical systems and differential equations in modeling complex systems across physics, biology, economics, ecological and epidemic modeling, environmental sciences, and neurodifferential equations, physics, informed, of course, neural networks, data to differential equation models, and etc. So there are a number of applications, of course, which we will look at today. So the event will foster knowledge exchange and collaboration. So we are glad that you are here, that you can join us. So what I decided to do for this session really is to, I must also, first of all, before I go into what I have to say, to thank the organizers, the local organizing committee from Stellenbosch University, Suriname University of Technology, WITS, and AIMS, and then also including NITHEX. You'll see that the name tags you are wearing about NITHEX, so I'll talk a little bit about that later. And from our side, I should acknowledge, of course, Dr. Ali Raza, who is also a postdoctoral fellow at Stellenbosch, who has really helped. Mr. Sibusiso Lukele, who is also the project coordinator in my office, who's been very helpful. Professor Francesco Petrocione, who's the director for NITHEX and also the pro-vice chancellor for AI at the university. Professor Andronicas Paliathanasis, who's going to join us tomorrow. He's traveling as well from Greece. Professor Eckhart Scotts from Suriname University of Technology. Professor Sege Meleshko, who's also joining online from Suriname University of Technology in Thailand, and then Dr. Petro Landi. If you can raise your hand so people can see you. I mean, we have students here, but of course online they may not be able to see you for helping. And then we've got Professor Hugo Touchet as well, who's the AI expert. So for those of you who are interested in the AI area, please feel free to reach out. And then Dr. Hades Dedricks is the head of applied maths, but he did send apologies for today because there is something else going on. It's a very busy time for us now, because our students, we are ending the year and there's a lot also going on in terms of trying to prepare reports and meetings and so forth. Professor Karen Therese Howell is based at AIMS, but she should be joining us at a later stage. I'm not sure if it's today or tomorrow. But AIMS is the African Institute for Mathematical Sciences. And then Professor Abdul Kara, I've not seen him, but he's probably late, but he's based at WITS, but also very supportive of the programs that we do here. And then Professor Ulrich Paquet is the director of AIMS currently, and he's been very supportive in most of the initiatives and organizing. And then Professor Khan Hui, who is our chair. Professor Hui, are you with us? We are raising hands. Oh, it's even cool that so just to say thank you so much. So if I've left out any other person, I just want to acknowledge everybody who's been supportive. So the workshop has got 3 themes. It's 3 days. And then in these 3 days, I'd really encourage you to engage and to really, see how you can, because the value add is really to the work you're doing, asking what's the value, why are you doing what you're doing, why are you, I know that for the students, I've got 2 of our students here, I think whom I should not expose now, maybe you can introduce yourselves later. They want to publish, want to write something, want to publish, but the question is why? Why are you doing what you're doing? What is the value add? And, what is the value that you're adding to the field? Any new knowledge that's coming out of that? So I think day 1 focuses on mathematical methods for the treatment of differential equations, and there you get different methods that are applied. Is Professor Karen here? No, I didn't see her, so I didn't miss her out. Yeah. So you talk about there's Lie symmetries and group analysis of differential equations, integrable systems and pan-level analysis, geometric theory of differential equations, and then modern techniques for treatment of these. And then day 2 focus on differential equations in natural world, in the natural world, and in physics, of course. So we've got themes there. And then day 3 focuses on modern computational approaches, which we'll look at as well. So having said that, just a little bit about, you will stop me when it's 5 minutes before, about the workshop. So you have that information about the university. So for those of you who've not been here before, so Stellenbosch University, we aspire to become a global, we want to be a research-intensive university. Well, we are actually, but we want to be amongst the top 100 by 2040. I think our vision is about that, but we also want to do research and advanced knowledge that actually helps to address some of the issues in our society. So from the mathematics point of view, if you're looking at this, it's also about trying to understand how mathematics can also address these problems that we face in society. And in most cases, when you look at applications for grants, they'll ask you, what is the impact? What is going to be the impact? What is the value? And it's very difficult usually from the pure maths side to answer that if you can't really relate to the applications in real life that you can apply these methods to, or whatever approaches that we're doing. So at the university, we do focus on people as well. So this workshop is one of the platforms that we organize, of course, to bring people together. But there are many things in the university that go on. We have a number of conferences. I think Professor Wee, for example, also organizes a number of conferences which take place, and the other colleagues in the department. But in the university, we have what we call chairs. So we have some chairs in maths, of course, engineering and other areas. So in total, we have 52 research chairs, and 21 of these are South African research chairs. And a chair is just, researcher who's funded with a group to focus on a particular problem over a period. I mean, it ranges from 5 to 15 years in terms of funding. We host something like, at this stage, we have 400 postdoctoral fellows that we host at the university. So this is an area where we are trying to raise. In fact, there's a call which is open currently for people who are interested in postdoctoral fellowships. And I was told that we didn't get many applicants. So I think it's an opening where if you are interested, if you can find a host, especially we push a lot the STEM areas, and maths is one of the areas that we are really pushing as well, the mathematical sciences. So if you're interested, it is something that you could do. It is important, of course, to identify a host early by then. And then, of course, we have a number of partnerships globally and everywhere else. in Africa and globally as well. As a university, rankings are important. So we rank second in South Africa, but of course we are still in the 300, 200. Actually, we've dropped a little bit in the 300 range band according to the Times Higher Education rankings. But it is something, of course, we're working on in terms of improving. And then most of our research funding comes from research grants, and we have a lot of partnerships, of course, where we collaborate with other countries as well. But the thing is, I think what's important there is that even to do maths, even as a scholar, emerging scholar, whether you're a student, whether you're a staff member, funding for research is important. So understanding what grant opportunities are there and what, where you can get funding to support your, whether you're doing a postdoc or research, emerging researcher, that's important. So this slide here just shows, the outputs. You might not be interested, but we normally, record the number of outputs we publish, because my job is about trying to get people to publish a lot so that we get more money, and then so that we improve our rankings, and then also trying to make sure we improve our impact. Thank you so much, Professor Abdul. We did welcome you in your absence. Yeah. So you can have a seat also in front. Yeah. Thank you so much. So the people come late have to introduce themselves, but we can do that later. All right. So on this slide, really is just showing you. So as a university, so if you go to, if you have, so there's a, this tool, this tool, if you go to cyber.com in your university, you can find, this is normally where you'd see like your own profile as well. But for the university, you see that our international collaborations about the outputs that we have produced during this time. So you have to look at the year that you're looking at. So in this case, you can see that around 56.3% of our publications are with international collaborators. So we want to increase that to 80%. Normally for universities that are very active and want to be highly ranked, they have a higher percentage of international collaboration. So for us, even this workshop is really try to connect people so that we can get people collaborating and increasing that, because it's quite low for a university of this size. And then national collaboration, 17.2%. And then, of course, you see there, where people publish single authorship and then only institutional collaboration. But what's important to point out here is you see that why is it that we push international collaboration? If you look at the field-weighted citation, the number right on your, I don't know if it's on your right, 2.48 there, your international collaboration helps to increase also your citation, and also your field-weighted citation normally is higher if you collaborate with other people outside your usual geographical domain and space. So at the university, we have a number of focus areas. So here I will not list all of them. But I think what's important for today is to focus on the mathematical sciences. And so you see that there's a number of areas that we have as a university. So here I just listed a few: the computer vision, pattern recognition and machine learning, fluid dynamics and modeling, numerical analysis and scientific computing, and then applied discrete mathematics. And then you will meet colleagues here who are leading some of the groups. Of course, we haven't listed the group on differential equations and symmetries here because it's newish, and then it is something that I have to, I think, register with the applied maths unit. But you see here algebra and model theory, and then there's categorical theory, algebra, discrete maths, dual theory, functional analysis, mathematical and theoretical physical biosciences, number theory and geometry. And if you go on our website, you'll find that information. I spoke about what the workshop is about, so I should just quickly jump into at least this aspect in terms of, so you know that with differential equations, usually describe the model, and of course the solutions, when you interpret them, actually should have meaning. But in this case, I just wanted to point out in terms of the historical notes, and I should blame Ali if I've left out anything, because he was helping me with the slides. But in this case, let's talk a little bit about Lie groups and so forth. So if you don't know from a historical point of view, Sophus Lie was a Norwegian mathematician. And he was a founder of the theory of continuous groups and the applications to the theory of differential equations. So his investigations are what led us to one of the major branches of the 20th century maths, theory of Lie groups and Lie algebras. Very interesting, actually. I think for those of you, how many of you here work in this area? Lie groups, Lie theory, anyone? One? Only one? Okay, at least we have some people, yeah, interested. It is quite interesting, but of course, yeah. And then so he was in 1870 during the Franco-Prussian War, after deciding to walk to Milan and hiking home across Germany. He had been arrested during that time, but he finished his PhD while in prison. And I think the reason here is to just also remember this quotation, and this is what he says, that I've taken things truly philosophically. I think that a mathematician is well suited to be in prison. That doesn't mean that I accepted freedom philosophically. In truth, the sun has never seemed to shine so brightly. The trees have never seemed so green as they did yesterday, when, as a free man, I walked to the railway station in Fontainebleau. So I think for me, the analogy is that, so yeah, so it's if you, to do this type of stuff, you do need time. You need time to focus. You have to cut down a bit of your social life sometimes, yeah. But it's really an enjoyable area, and I would really encourage you, for those who might not be familiar, to actually do some readings on this. And then the other key person I think that's important to note, you see also there's quite a bit around conservation laws and invariance theory and so forth. Amy Noether lived in the period 1882 to 1935. She was a German mathematician who made important contributions to abstract algebra. And then she discovered Noether's first and second theorems, which are fundamental in mathematical physics. And for those of you both in physics and maths, you find these applications interesting. During that time, of course, women did not have equal access to research or access to education as she did. So she audited classes and finally completed a PhD, of course, which was taught by David Hilbert, Felix Klein, and Hermann Minkowski and Karl Schwarzschild at that time. So, and then other women who've contributed to this area. You've watched this movie before, right? How many of you have watched it? Only two. Okay, yeah, it's quite interesting to see. So it's a very interesting movie, but it also shows you there's been quite a bit of contribution. So the West Computers, which is the West Area Computing Unit, these ladies, actually, the story here features these African-American female mathematicians who worked as human computers at the time. From 1943, I think, up to 1958. So there were a subset of hundreds of female mathematicians who began careers in aeronautical research during World War II. It's a very inspiring story, I think, to understand the contribution that women have made as well to mathematics. So in terms of, I will not go into the definitions, because today you will get a lot of the presentations normally start off by defining what you mean by a group. And the properties of the group, both the closure property, associative property, identity element, inverse element, and then what it means to have a subgroup, to have an abelian group. And then the other part is people will also describe Lie group transformations, that as well, because I think in the presentations you get this. And then the different terminologies that are used in terms of Lie groups. So you can find this standard text really around, what do you mean by linear group, general linear group, spatial linear group, complex spatial linear group, the rotation group, and then what do we mean by Lie algebra from a definition point of view. And then, do I have enough time? Yes, I can. How much time do I have? 10? 10. Okay, 10 is enough. Okay. Also, what we mean by Lie algebra. So we define a Lie algebra and Lie brackets and so forth. And we also use a number of properties that are there. So I think in terms of remarking on this, a Lie algebra, of course, would normally be defined over the real field and complex field, and then a differential equation that admits the operators, when you define them, admits a Lie bracket, and then you have properties that these Lie brackets would fulfill. And then you have a continuous Lie group that can be assigned to a corresponding Lie algebra, and then a Lie algebra, of course, can be assigned to a corresponding Lie group according to Lie's main result, which is given in that text, that is quoted there. You can find that text available online as well. And then when we talk about differential equations, we know that they arise from many phenomena, and I spoke about this area, whether it's in physics, I think biology, astronomy, cosmology. I mean, describing all our systems, biology, ecology, economics, engineering, etc. And then the methods, there are various methods that are used to solve. Of course, if you come to differential equations, there are many methods, and then you have to think about why you are using a particular method. Some methods will work for certain cases, some may not. And then also we use, because now of the advancements in terms of computer technology, computational technology, there are a number of tools that you can use. So in terms of Lie groups, we do normally use reduce. You can use mathematical mapo, just to code what you're doing and then to try to solve more complex problems. And then applications of these symbolic calculations, can be used in group analysis and in transforming equations into simpler equations that you can work with. So this is just and this is just an example. Again, if you have an ordinary differential equation of order n there, that admits a one parameter Lie group of transformations that's given in the second in that line, second line there. Sorry, I don't have a pointer to add. Yeah. And then if you have this infinitesimal operator generator, then apply to that equation, the first equation, the differential equation you have, then you get an extended infinitesimal generator, which you can then use to find what the Lie symmetries are. So having said that, I think our group at Stellenbosch University, we have had quite a bit of 2025 was not too bad, but so we've done a number of things, I think, both in the mathematical physics area, and I think Andronicus is coming tomorrow, but we did something on the geometrical interpretation of the algebraic properties of second order ordinary differential equations. So you can just check that out in terms of some analysis that was done there. And then with, there was also a paper done by, I think, this is Adil, Peter Leach, and Megan and David Day. So this is Megan Govinda and David Day at, this is at, I think it's a DUT group and another group at, it's not WITS, it's DUT actually. All of these are DUT. Well, and UKZN, Peter Leach, I think is at UKZN, on linearization of second ordinary differential equations. I think what I asked Ali to help me with was to look at what has been done recently. I'll skip this one because this just defines, the applications to PDEs as well. And then recently also we've seen quite a bit of, there are lots and lots of papers which are being produced, but in terms of what we're doing here is, for PDEs, we've been working on also some PDEs which describe physical systems. So constructing exact and invariant solutions, and then the classifications of these equations via symmetry algebras. And recently, we just managed to finish off the first piece of work on the Lie symmetry analysis of rope webs and periodic webs and various analytical solutions of nonlinear diffusion equations with applications. And then with Matthew will join online. He's been just focusing on constructing exact solutions to systems of reaction diffusion equations. Matthew is a postdoc as well as Ali, but Matthew is based in Canada currently. And then with Kevin Duffy, I think is also going to join us online. So this is just our local group. We've done this type of work, which you can find as well. So I'll just leave these slides will be shared. It's just to show that we've been trying. And then I see that we also have our two students behind, Kasey and Dumisane also, who have been focusing on, they're starting their PhDs now, but they did their masters last year, and are also focusing on applying, they will do also the symmetry analysis in the problems that they're doing, but applying them to the modeling brain tumor as well. And then I asked a colleague, because most of the people do maths and modeling brain tumors, so I asked, have you ever seen a cell, or you just look at it from a book and say, oh, this is how it looks like? So we are really privileged to be at the university where we have very good equipment, which, one of the colleagues has agreed to actually do the scanning of some of the tissue from the tumors, which they can actually look at. So at least they can use some of those images at some point in their work as well, as they do the analysis. And then this Stephen Anko has also done quite a bit here. I just asked Ali to put what has been done recently so he can share this in terms of the work. There's also, I'm sorry, I have to close that here. Willy Herrmann as well, who's done quite a bit, including on symbolic computing. So if you look at his work, that is also helpful for those of you who are interested in this work. My slides are not moving anymore. Okay. Then Sergei Meleshko, who will speak, I think, I'm not yeah, he's going to speak as well, has also done quite a bit, but you can also see the work that they're doing in terms of integration of ODEs with related arguments. And I was just told yesterday that they've also been applying through interactions. Last time, I think Sergei met with Professor Hui, and now is very interested in biological systems. So he had asked to just mention that as well. And then I think Professor Abdul Kara, who's here from BITS as well, he's done quite a bit this year. I see, yeah, 2025 looks good for many people. I've been counting. And then I think Andronicus, also who's going to join us tomorrow, is more on the generally, he's in the physics side, cosmology, general relativity, and so forth. So he's also been busy. And I saw also Professor Gandarias Marias, so she's also done quite a bit in the year. So all these just show you. Professor Sachin Kumar, also who's joining us. Thank you so much for joining us. So for those who are, students who are interested, at least all the people are here. They are not sort of abstract, approachable, so you can approach them and ask them to. And then Alexi is going to join online. Yeah. So I haven't seen him here. Okay. Then Professor Zaman as well. And I think Masood Khalik is based at Northwest University. Is anyone working with Professor Masood here? No? Okay, but he has a lot of students whom I've seen in the past, Francesco Oliveri, and I think those are the people who've worked in this area. And I'm sorry, I'm not, I didn't focus on, I focused on, my job is to focus, of course, on what the university is doing, which I've done, but I also tried to just show you a little bit around what are we doing in this area. And there is a group that's emerging here. So with Professor Abdul, we've been trying very hard to establish something also on our side in terms of working on symmetries, differential equations, and symmetries at Stellenbosch. So with those words, I hope I've encouraged you and inspired you, but we also look forward. My appeal is enjoy while you're here, but also try to network, make it worthwhile. And ask hard questions, don't feel shy to ask and interact. Some presentations will be online and some will be here. I understand also from a logistical point of view, I don't know if Ali, if you have any announcements, but basically if you are here, the bathrooms when you come out are on your right, okay? You can walk around. It's a very safe place to walk, but just make sure you have your laptop because we don't have of course, if you're having tea and whatever, you can leave your things here. But if you are going to go away for a walk, don't miss a session, but you can walk around. It's a small town. Basically, the shops are within walking distance. And then I think what we are planning is to have something tomorrow, maybe a cocktail if things work out. So that you will get instructions once we know where that cocktail is. Again, it will most likely, hopefully, be walking distance. So you don't need to hire a cab. So when we say walking distance, for us, 10, 15 minutes, we walk. So I know some people might say, oh, no, I need a cab. I don't have transport. But usually we walk to places. It is very hot, so just make sure that you drink a lot of water. And then if you need anything, let Ali know, because Ali is our program. He's the organizer. Basically, I've left everything to him because I have to also do other work. And Professor Abdul Kara is the academic person who, if you need something, you help. And then we've got our colleagues from the maths department who are here as well, if you need something. So otherwise, enjoy and best wishes. And thank you again for joining us. We really appreciate your support. Thank you. Mm-hmm.
Thank you so much, Prof. Moyo. As an ecologist, I was very proudly following along your presentation and understanding the numbers until you taught me that it's not Lie algebra, it's Lie algebra. So you ruined my hopes and dreams of ever being a mathematician. Let's give her another round of applause, please. Thank you so much. So for our next keynote, actually, sorry, before I get onto that, I have been approached about getting some extension cords, and they are working on it, so please just be patient with them. So for our next keynote, we have Prof. Abdul Hamid Kara. Thank you so much. And he is spearheaded his career at Wits University, right from a junior lecturer to a professor, and spent 1 year being a school teacher. We take it that didn't go well if you only lasted 1 year there. He's going to be talking to us about invariance conservation laws and difference equations. So as an ecologist, please laugh with me and not at me if I get either name spellings and pronunciations wrong or other pronunciations wrong. And thank you so much, Prof. We're looking forward to it. I've also been told if I tell lame jokes, you'll laugh at them.
This guy's a star. Where I was. Thinking, I don't know all of that, and of course, you see this traffic coming to Stellenbosch, but I didn't really that way.
Yeah, we all
I'm sorry about it. No, but I need rain.
The Protea Hotel. I don't know why they decided to have two Protea hotels. So you notice I didn't even have my tie on. You know? Now I need to learn how to use this. Okay. Okay, so when I decided the specific aspect of symmetries, I thought, let me choose something that I had worked on with some previous PhD students and so on. So instead of going down the differential equations route, I'm going to speak a little about difference equations. So there's been some development, well, not some, there's been a reasonable amount of development in the area of the application of these Lie symmetry methods into difference equations, the discretization of differential equations. A lot of the work has been done by two groups. One is the Peter Hayden group. Peter Hayden, I think, is still based at Surrey in England. And there's Pavel Winternitz, who is based at the CRM in Montreal. So they really developed this, this method, or at least the application of symmetries to discrete equations in a detailed way. Well, Pavel Winternitz worked also with the Italian Deccio Levi, and they did a large amount of work in that. The trouble with discrete equations or difference equations, we know where it arises, or we think we know where it arises. And the starting point of difference equations, to me, seems like, you know, when you're doing numerical analysis and so on, you're trying to discretize your equations and so on. So you automatically, you end up with difference equations. So that's one aspect, or at least that's one place where you would find difference or discrete equation. When you get into the realm of difference, of the application of these Lie symmetries, these transformation groups into those kind of equations, the question is, how do you adapt it? Because discrete means exactly what it says. It's discrete, right? Differential equations are continuous. And you're going to ask this question, if I've done my job correctly. So let me predict your question. You're dealing with discrete equations, and I keep thinking I gave this talk already. So not long ago, I gave this talk at the NILSI, the weekly colloquium at NITEX, where I looked at the basic aspects of the application of symmetries, so where they come from and so on. So the one little phrase that I like to always pick on is, when you're dealing with symmetries of differential equations, you're looking at continuous transformations. You see? So what's happening then is I'm going to spend a little time. It all starts where you're looking at manifolds, you're looking at points on a manifold, and you're transforming these points from one point to another. And the important thing is continuously. You see? Now you can, and it applies on differential equations. Differential equations they give you solutions which are perhaps curves on a manifold, continuous curves. So symmetries, continuous transformation seems to work well. Continuous, continuous. Now you've got these discrete equations. And the question is, what kind of transformations are you looking at now? Because you need to essentially deal with discrete transformations. It turns out that what I'm going to try to introduce here, or just relive some of those ideas, is the application not of discrete symmetries, rather the same notion of Lie, continuous symmetries on discrete equations, right? So you need to keep that in mind. That's the one aspect. Now, another aspect that I troubled Ali with was to produce some of these pictures, is that you're dealing with manifolds, nice manifolds. Your differential equations or your solutions lie on these manifolds. So it's all very well to introduce a method that works for discrete equations or any other kinds of equations. The point is, when you go back to the manifold theory, which is where all things start, what must your manifolds look like? You're dealing with discrete, you've got points. I mean, these are now points, discrete things, right? So what's your manifold like? So you'll notice that in the initial aspect of my talk, I'm looking at some pictures describing the notion of, and it's from an art. I stole these pictures from an article in the notices, one of the previous notices of the AMS, where the authors there do speak of the notion of discrete differential geometry. The whole notion of manifolds lie in differential geometry. And so this whole nice new area on discrete differential geometry. So it was revealed to me that this works well for you. And I grabbed this thing, and I hope that we can pick out how the notion of discrete manifolds work. And then maybe it will fit in with the notion of discrete equations, but I still go back to one thing. This Lie symmetry applications on whatever is a notion of continuous transformation. Right, so if there's lots of details and so on, I always tell the audience, just forget about the details, but just look at the ideas of what this is about. Okay, so, I should use this, right? On the mouse. And now it will work. Wow, but it's looking, there's a time delay. Okay, so a lot of what I'm saying initially, Professor Moyo had discussed where these ideas came from, Sophus Lie and so on, the amount of work done in these areas and so on. So this is a picture that I've troubled this man to fit into my talk. So these next 3 slides is an attempt to show how these notions of continuous manifolds then are interpreted or construed as equivalently into discrete forms. So it might still be a bit confusing to see where do these things come from, even in these pictures and so on. But the nice picture is essentially this one. Now, it's this notion of, I mean, you've got these continuous things that one normally builds, but this little picture says, oh, well, suppose we replace continuous concrete structures or something like that with these scaffolding kind of pictures, and then you suddenly get these little jumps that you could construct. So you've got these points that connect, and they look like discrete manifolds and so on. So when the authors discuss the notion of discrete differential geometry, they're looking at what could physically be interpreted as these discrete manifolds that exist out there in the real world and so on. And when you're looking at these, for example, equations that arise in your numerical analysis, right? When you discretize an equation, you've got these points that arise, and if you connect these points, you end up with things that may look like that, okay? That's the one aspect of the discrete equations. Now, when you get into, try to recall how the Lie symmetries work. in differential equations, or in fact, even in algebraic equations. You're looking at transformations, you're looking at change of variables. Essentially, this is what it is. You're looking at particular kinds of change of variables, which when you substitute into your equation, it leaves the equations invariant, unchanged. And when you can do that, you can find these transformations that do that, it gives you various things. It gives you the ability to reduce equations, maybe to transform equations, to categorize them, to classify them, and so on. But it all hangs around what kind of these transformations exist. So a particular differential equation may not have a single one, maybe have a whole class of these transformations that leaves the same differential equation invariant. And it turns out that once you collect all of these, they have all kinds of properties. Besides the fact that you can reduce equations and so on, algebraically, for example, when you collect them, they form Lie algebras, they form Lie groups. So there's all kinds of nice things that happen outside into algebra and geometry and so on once you classify these things. So when you get to discrete, so if you get a discrete equation, suppose it arises from a previously continuous differential equation. So I give you the KdV equation. You might discretize it for some reason, maybe to deal with it numerically, right? So one of the ways in which you could derive a discrete differential equation is to say, wait a minute, I have my continuous equation. I know all the symmetry things about it, all the transformations that leave it invariant. Can I construct the equivalent discrete equations in such a way that when I do the symmetry analysis, the symmetry algebra, the set of transformations that left the differential equation invariant, can I transport that too? So you want to leave your transformations the same. And when you can do that, you really have lots of power in that. But it's a lot of work. So you got a differential equation, you have a discrete version of it, either through numerical analysis, or you might construct a discrete equivalent by saying, well, I want to construct the differential equation, the discrete version in such a way that my algebra of symmetries, my algebra of transformations remain the same on that side. So in that too, quite a bit of work has been done by Winternitz in this group. So there's always that there's a number of ways in which we could pick up these discrete equations. Once you've got that, let's speak about these continuous transformations of discrete equations. So this is where it gets technical. This is the part that, like you, I will not like. I threw this in some time ago in my set of slides that if you want to get into the notion of discrete equations, where they arise, what they like, and so on, there's YouTube, the power of YouTube. Okay, so this is where we started. So here we get into some technical versions, definition of a difference or discrete equation. So 2.1 is a capital nth order discrete equation, right? So you've got in differential equation, you've got second order, third order. So this is just a definition that we'll call a difference equation of nth order if it looks like that. Finally, when you get a solution, you would want your solution to look like 2.2. That'll be the way your solution will look, an explicit solution. Now, what do we do in symmetries? We look for transformations that leave things invariant. So you're taking points and you're transforming, continuous transformations, right? So when the notion of these transformations was introduced onto discrete equations, it turns out that we needed this little operator around which all of this theory on discrete equations will hang on, and that is 2.3. So we've got the shift operator that just says, first of all, that the shift operator transforms n to n plus 1, so one point to another point. That's fine. That's a straightforward transformation. But what do you want to do with it? You want to keep things invariant. So the operator that you want unchanged in whatever you end up with is this operator. So this operator said that if n transforms to n plus 1, when it operates on your variable, your dependent variable, you want it unchanged. So this statement here is essentially saying that when you change your point, you want your output to remain the same, invariant, unchanged. You notice the notion of unchanged or invariance is coming in, so that we end up with a statement like this eventually. Okay, so you just want things to also remain unchanged as you go along. Right. Now, you might have noticed from the previous talk that when you have these transformations, I'll spend just 1 minute on that. These transformations, these Lie transformations that we speak about in this area of applications of Lie symmetries on differential equations says the following, that if your transformation satisfies certain properties, we classify them as a Lie transformation, and turns out that every such transformation can be represented in a vector field form. And the fact that you can, and why do you want to represent it as a vector field form? There's a way of doing that. Once you know it satisfies certain properties, then all your calculations suddenly become easy. So when you apply or you want to find the transformations that leave a differential equation invariant, you go via the vector field version of the study. It makes it all very nice. This is due to Lie. This was the classic application of Lie's work, or the real profound depth of Lie's work, is that you could rewrite these things in terms of vector fields. And it turns out that when you're defining the transformations, the invariance of difference equations, the equivalent operator in vector field form is your vector field, what we call a symmetry generator X. So every vector field written like that represents a one-parameter continuous transformation. So when you write in vector field form, you tend to lose the roots of what it represents. But just keep in mind, this vector field is a nice, convenient version of your one-parameter transformation. And when you do your calculations, when you're finding things that leave a difference or differential equation invariant, we end up with the vector field version. And when you've got the vector field version, you can do all kinds of nice things. So for a discrete equation, that's your vector field, that's your generator that will eventually leave your discrete difference equation invariant. And the identifying equation, this condition, the symmetry equation that from which you will pick up these things, these capital X's, these vector fields, is 2.4. So all 2.4 says that if you want to find the vector fields that leave your discrete equation invariant, call it capital X, it needs to satisfy 2.4. And it needs to satisfy 2.4 on your discrete equation. So your transformations must be unchanged, but must be unchanged on your equation. And once you've got those vector fields, then we can start doing nice things with it. So, and this then is just merely saying that once you've identified your condition, you go through a set of calculations and so on, and you end up with a generator like that. I'm not going to get too much into the details because that we can always discuss afterwards. But this is essentially your starting point. Right. Let's stop there for a moment. So that's vector fields that leave discrete equations invariant. That's how you find them. Lots of calculations that will follow after that. And if you want to be a bit famous, you want to make a bit of money, something, develop software in that, because there's lots of software these days for finding vector fields that leave differential equations invariant. Discrete equations, that's something you can do. Young people, you can do it. Okay, let's stop there. And an aspect that is related to symmetries of differential equations is the notion of conservation laws, first integrals. I always like to, and that's where Professor Moy spoke about Emmy Noether. She was the pioneer that linked the notion of these vector fields leaving systems invariant in the construction of conservation laws. That was really the Noether theorem, 1918. That's essentially what she did. But for that, you need a definition. What is a conservation law? So mathematically, your conservation laws were that essentially you can write your differential equation in conserved form, okay? Or closed form. For those of you in physics, you use different definitions. You call it closed form, sometimes you call it conserved forms and so on. But essentially, you mathematically have a definition that finds conservation laws. Sometimes these are physical, and that's what, in fact, what Noether did, was she related them to physical conservation laws, that your time translations were associated with conservation of energy. Your rotation was associated with angular momentum, things like that. So that's essentially what Noether's theorem did. So what is the notion of, say, first integrals in the arena of discrete equations? And that was a definition, again, I think due to Peter Haydn. What do you do in conservation laws? You want things to be conserved. Conserved means what? Unchanged. Go back to the operator S, that is moving your points around, that curly S that I've introduced. So in that same notion of curly S, we're saying that if your function, if some function is unchanged, so the operator S is shifting things. So it's shifting things on the function, but shifting it in what way? To leave it unchanged. So that's the, you notice the operator S on your phi is still phi. It's unchanged. So that was the equivalent definition of conservation for discrete equations. So that then if you open up the definitions and so on, remember what S does, it takes n, transform it to n plus 1, etc. So sorry about that little thing there. So 2.7, essentially the second line says, that's how you find your functions phi, which identifies your discrete equation version of first integrals, conservation laws. Why was the notion of first integrals so nicely or practically linked to the notions of vector fields that leave differential equations invariant? You see, one of the mathematical things to do is, mathematical applications of symmetries is to reduce equations. Conservation laws, mathematically, besides the physical aspect of it, also allows you to reduce differential equations. And it was shown that when you can reduce this way and that way, and put the two together, you end up with reduction twice. So now you have the power of reducing your equation twice as opposed to once. And what do we do in differential equations to solve? We reduce. And if we reduce twice for free, there it is. We just have to find these first integrals also. And it turns out, and that's a little work which my PhD student a long time ago did, is to actually say that we can find these vector fields that leave discrete equations invariant. We can find these first integrals like that. And the question is, for discrete equations, do you also get double reduction? And it turns out that the answer is yes, we do get that too. Right, so whatever follows here is just saying, eventually you put all this together, you have a method for doing these things. So what I've spelled out here is just that once you've identified a definition that allows you to find phi, that gives you the first integrals for discrete equations, you need to go through a set of detailed calculations. Again, it's a method that was developed by essentially Peter Haydn into finding these first integrals for discrete equations. So this is just the method. And eventually your first integral will look like that if you go through the calculations. The function g of n is just like your constant of integration equivalent that comes up, which you can find by just substituting things back and so on. So we've got two parts then. Vector fields that leave discrete equations invariant, continuous vector fields, continuous transformations, not discrete. That leaves discrete equations invariant, and you've got a method for identifying first integrals of the same discrete equation. And we'd like to put eventually these two things together. And once you get the vector fields of the discrete equations, do they do nice things? Or algebraically, are they nice? Nice meaning, do they form Lie algebras? Do they form Lie groups? And it turns out that actually you can extend your definition of your Lie bracket to these vector fields also, and they satisfy closeness. They form Lie algebras and so on. The Lord has been good to allow us to extend this even to discrete equations. Right, so this is just repeating the definition, and then I was supposed, oh, where's my example? So I'm just in a detailed way going through some examples as to how you've got your discrete equation, you're applying your symmetry condition, etc. This is just a method of reducing an equation. Perhaps I shouldn't, I'm thinking whether I should go into the details of that. So once you go through your reduction process, then you end up with a solution that looks like that. And you would then go into starting with a condition like that. This is just a method now of if you do. Don't be rude. No, the reason I'm just joking. The reason I'm saying that is there's a new member of staff in our department that she walks around with this with like a little bell. Sorry, I have to spend this. It's just interesting. I'll spend half a minute. And she also is not far from it. I know exactly where she's coming from. She says, we're going to use that for telling speakers, cling, 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 5 minutes, in a really irritating sound. I'm done by then. Okay, so this procedure then, if you need to, after the talk or sometime during the course of this workshop and so on, if you want to discuss details, please come and see me. But I don't want to get into the details. So the real idea of the method is, here's a discrete equation, certain order. There's an algorithm, a procedure that has now been established to find the vector fields, continuous vector fields that leave it invariant. There's an algorithm to find first integrals, and together they do the nice things they do as in differential equations, reducing your discrete equation, finding the algebras that keep it invariant and so on. All the nice things do happen. And so essentially a recent idea, when I say recent, maybe last 20 years or so. And the geometrical aspect, differential geometric aspects, sort of looked like it was a bit sketchy and not complete, but there are notions, there are works out there, which is not really my work, the notions of discrete differential geometry and so on. So it fits in with the whole notion of manifolds and so on, because everything here is about just manifolds. So that area has also been developed independently and seems to work all very well. So there's quite a bit of work for anyone who's interested and energetic enough to say that, well, how can we now relate this directly into the notion of discrete differential geometry also? It can be really interesting. And of course, the notion of discrete equations is very important. It's more important to a lot of people, especially those working numerical methods and so on. Numerical, when you take differential equations and rewrite them numerically and so on. So this is essentially then just going through an example that says, well, given a specific example, we can find, or I'm just going through this, you end up with calculations that look like that. The calculations eventually are simple, but detailed and so on. And that's why if someone can eventually write maybe code on this, it will be interesting. And I suspect it can be done. So here's an example. I mentioned an example early on. So you end up with a vector field that would leave the initial example invariant, and it looks exactly like a vector field that you would find in differential equations. Its variables look discrete. You've got your n's, and which is really your points and so on. But the structure is a vector field. And a vector field has an equivalent one parameter Lie group of transformation, continuous transformation. So the representation is a continuous representation, but its application is on discrete equations. So just a little comment, which I think I said you will probably ask, but if you're not going to ask, let me just speak about it. Is one of the questions I get is that even in differential equations, well, how about discrete symmetries? Now, there are lots of discrete symmetries out there. Reflection is a discrete symmetry. Your equilateral triangle is rotationally invariant, but discretely. So like you have got to rotate it by 120 degrees before it looks the same. So it is not a continuous invariance. It is a discrete invariance. We're not speaking about that at all. Okay, that is work. You get differential equations that are invariant under discrete transformations, but that's not me. That's not what we're speaking about. We're looking at continuous, like your circle. It's continuously invariant. Okay, and you get many other examples beyond your nice rotation and so on. So this was a procedure just to show how this applies to discrete equations. For the same example, once I've got the vector field, I can then construct my first integrals. It's again the standard procedure that starts off with the definition of first integrals for discrete equations. And for this example, we end up with just to jump to you end up with a first integral that looks like that. Okay, so you've got a first integral, and you've got a vector field that leaves it invariant. And what we did do very briefly is to show how we can doubly reduce the discrete equation. I've been told to keep quiet now. So I'm going to jump to, so this is the last comment, that it has been applied to the notion of double reduction of discrete equations as we do in differential equations. These are the usual this is about continuous symmetries on continuous differential equations, which is some standard text. Peter Haydn really mooted this idea of symmetries on difference or discrete equations. And of course, Pavel Winternitz took it on further. I'm not sure if I mentioned, oh yeah, there, the second one, Pavel Winternitz and Decio Levy. They did quite a bit of work on discrete equations. You might know Shah Devan, who works at the Ramanujan Institute these days. He once came to our first conference in Johannesburg a long time ago. He's still active, I think. Yeah. So thank you very much. I'm sorry for coming in late. And I know I always say that when I wear a tie, something's happening. And I wasn't being rude. I was.
No, you weren't being rude. One or two questions. If there's anything online?
If it's not a question online, and Sergey, we can maybe ask him to unmute, and I will just hand you this. If we can, if you also quickly disconnected, we can have one so
So there's a question online.
So is anyone working on the conservation law for this video?
No, so if there's any questions, yeah.
So that's what he's asking. First online. Okay.
May I give comment?
Sergey's got it.
Yeah, it's Sergey Mileshko. Actually, about these topics, first time I heard, in 1987, it was much more
That one.
before. Hello, can you hear?
Sergey now, can you maybe speak again?
I'm sorry.
Can hear you.
Sorry, may I talk?
Hi, Sergey. See, Sergey.
Oh, okay. I wanted to give comment because first time that I heard presentation in this area, it was given by Vladimir Dorodnitsyn much earlier than Peter Haydn did, and much earlier than Pavel Winternitz started working on this. Actually, I think that Pavel Winternitz joined to Vladimir Dorodnitsyn group, not Dorodnitsyn joined to Pavel Winternitz group, quite opposite. So it was in 1987, much earlier. So I just wanted to say, and in 2010, it was published in English, his book. So I want to give this comment. And you did not mention him, so I want to.
Oh, so can you hear me? Yeah. So Sergey, in fact, I'm aware of Dorodnitsyn's work, but I didn't realize that he's done this before Peter Haydn.
No,
it was
much
interesting.
Earlier. Much earlier. So Vladimir Dorodnitsyn, as I told you, that first time I listened in Ibrahimov's conference, it was before his coming. Ibrahimov before came to Johannesburg. It was in 1987. It was first presentation in this area that I heard. Later he published book. Now he is my collaborator. So then I want to say, please, next time when you present, please.
I will do that. Thank you.
Thank
you, Sergey. It's good. And we were hoping you were here.
I hope.
We have good weather.
But...
Thank you. Nice to chat with you, Sergey.
Yeah.
Is anyone doing sorry. Not that I know of anymore, to be honest. Even those people that I worked with, like Mensa, hasn't done anything recently.
Okay, so conservation laws.
Oh, no, your friend Akhtar might be doing something.
No, I think he did not did any conservation law for the discrete equations.
Okay. So I don't know of anyone right now.
Okay, so if we going to find the discrete symmetries for the discrete equations, so the method will be same, or is it
No.
or is another approach?
The trouble with discrete equations, even in differential equations, it seems to be guesswork. There's some work done by Tuba Feroz, who's done discrete symmetries of differential equations, but I don't see, there's no sort of algorithm, no standard procedure that you can now apply elsewhere. So I don't know anyone who's even got into discrete symmetries of discrete equations. Maybe it just doesn't work very well. Welcome.
Thank you so much, Prof. Promise you I can take a joke.
Yeah.
Oh, no, you can do it while I talk. So thank you so much, Prof. Next, we have Prof. Sachin Kumar, who's visiting us all the way from Delhi. Well, actually from the Protea Hotel, but we know traveling time is the same. Just it takes the same to travel from the Protea Hotel as from India. So he's well recognized for his research with over 150 papers and has received India's top cited research award twice, which is a great achievement. Well done. And he's going to be speaking to us about Payne-Levy. If I got that wrong, it's Pietro's fault at the back and Hugo's fault. Was it right? Right? Payne-Levy analysis and higher order rogue waves. Thank you so much, Prof.
Thank you.
We're here for a language class. Can I put this on you?
Yes. First of all, thank you so much for the invitation for this wonderful workshop on the dynamical system theory modeling and AI, and which is held in the Stellenbosch University. And I'm really appreciating the Sibo Moyo and the Professor Kara and the organizing team to organizing this wonderful workshop on this dynamical system. So as the previous two talks, the Sibo Moyo and the Professor Kara is talking about the Lie symmetries and the group of transformation method. I've already worked on this topic in the last 15 years, and I supervise 5 to 6 students on this Lie group of transformation method. And it is a really very beautiful method if you have a highly nonlinear evolution equation or a highly nonlinear partial differential equations. If you have the 4 independent functional parameter, so then you can reduce up to the ordinary differential equation and finding the solutions. Of course, as we are aware of that, the nonlinear ordinary differential equation is easily solvable as compared to the highly nonlinear partial differential. So this is the beauty of the Lie group of transformation method. But today, my topic on the Payne-Levy analysis, the higher order rock waves, and the dispersive soliton for a new generalized nonlinear evolution equation using the Hirota and solitons method. So in this topic, in this presentation, first we constructed a highly nonlinear 3+1 dimensional nonlinear evolution equations. First, we check the integrability of the constructed equations by using the Payne-Levy analysis. And after that, we show the higher equations solutions. Because as we know that we have no idea to finding the analytic solutions of a highly nonlinear partial differential equations. Because up to the graduation level and the PG level, we have no idea how to finding the solutions of the nonlinear equations. So there are the so many analytic method to finding solutions of that nonlinear partial differential equations. Suppose we are talking about the Lie symmetric method, the Hirota, inverse scattering method, the Arbex transformation method, generalized exponential rational method, generalized rational exponential rational method, and many other methods. The researcher working on these methods. So the topic of the content is the importance of studying why we are studying the rock waves and investigating the 3+1 dimensional evolution equation. First, we check the integrability, use the transformation, Hall-by transformation, reduce the bilinear form. After that, to finding the solution of n rock wave equation. And the same things we are doing for the another 3+1 dimensional KdV equations. So water waves. The research on the water wave has the important, significant attention across the science and the engineering. And we are aware that there are the different types of water waves. First, we are talking about the shallow water, the mild waves, and the strong waves. The strong waves, like just a rock waves. Sometimes we call it as a monster or a giant waves. And there are the many applications. Now, suppose we are talking about the waves here. These are, the point is crust is A and the B. And this is the wavelength, and the crust, the torque is so this is the solitary wave combinations. What is the wavelength and the highly amplitude occur in the oceans and rivers. So what is the water waves arises in the oceans and the many rivers and the coastal lines. Why the coastal line is so important? Because the coastal lines protect from the strong oceans and to create the beaches and the many other things. Now, the porosity is so important. It's a characteristic of the porous material is which is the dimensional measure the present the amount of the empty space within the materials. It expressed as the ratio of the volume of the empty to the total volume of the material, because it helps us the soil protect and the rock mountains absorb the waters. This is the main important thing of the porosity. The importance of the studying why we need the rock waves, because sometimes we call the rock wave as a strong waves in the oceans, and the rock wave also known as extreme on the most are rare and unpredictable ocean waves that pose serious threat to the human life and the marine operation. So the first figure is showing that this is the shallow water waves, and the researcher working on this type of equation. This is the 3+1, the KdV equations and the Kp equation, Jimov equation. This is the mild waves, and the researcher working on this wave. But this is a monster or a giant's waves. So it is not easy to finding the solution of this type of waves. So a key application of this research is the improvement of the marine safety, and the study of the nonlinear wave dynamics focus on the rock waves, as their wave cannot be explained by the traditional linear wave equation. We finding the solutions of the linear wave equations like the wave equations. The concept of the rock wave also find relevance across the various disciplines, including the nonlinear dynamics, fluid dynamics, and there are many other areas. So one of the most important example, just when we are the Malaysian Airlines flight MS-370, which is disappeared on the March 8, 2014 during its journey from the Kuala Lumpur, Malaysia to the Beijing, China, with the 239 pupils on board. So the track of this airlines from Malaysia, Kuala Lumpur to the Beijing, China, but after the within a half an hour, the plane disappeared, and the crash into the ocean powerful natural force. And this is the one of the most here the path of the flight is go to the Kuala Lumpur to the Beijing, but after some time he loses the contact, and after many searches of in the Indian Ocean, the sum of the particles of the crest plane pieces in this region. So it may be a main important. This Malaysian Airlines is destroyed by the rock waves. So that's why we are studying the rock wave. Why we need the study of the rock waves? Because the rock waves is very highly powerful, strong waves, and sometimes we call it as the giant waves or the monster waves, and which are massive, unpredictable ocean waves that can arise over the 20 meters high and appear suddenly in the rock waves sea highs. So I'm taking here the first example of the three-dimensional evolution equations. This is the linear combination of, it's a combination of it's a combination of a Hirota bilinear equation and the Kp equations. Suppose I am constructed this nonlinear evolution equation with the 3+1 3 plus 1 means is x, y, z, and t is there. 3 is the spatial coordinates and 1 is the temporal, means time variable. And the lambdas are the real parameters. And here constructed, when we choosing this lambda 1, 0, lambda 2, -1, lambda 3, lambda 4 is equals to 3. So this equation converted into the Hirota bilinear equation, which was already solved by this the Liu and Zhang in the Applied Mathematics and Ladder in 2019. And the combination of lambda 1, lambda 2, if we 1, lambda 3, 3. So this equation is reduces into the 3 plus 1 Kp equation. So this equation is a more generalized equation of this equation, of these two equations. The first, if we are constructing any nonlinear partial differential equation, so first we check the Panay-Levy, apply the Panay-Levy to check the integrability. So we use the field is expected by the Lorentz series with the G as an analytic function. We are using this combination and substituting in the previous equations in the main equation. So we calculate delta by resembling the dominance term with the leading order, where the highest order singularity we are occur. So we will get the dominance term. The delta is equals to -1 and the U0 is equals to 6gx upon lambda 3. So we get the resonance because we are talking about the 3 plus 1. So they are the 4 independent variables. Of course, the resonance having the 4 integers, -1, 1, 4, and 6. So we get the expression Uj explicitly. It means Uj having a solution for j is equals to 0, 2, 3, and 4, and the arbitrary choices j is equals to 1 and 4. So therefore, these resonance satisfy the condition for the compatibility identical. So this shows that the equation 1, this equation is integrable. So it means if the equation is integrable, so then we can apply the Hirota method or we apply the bilinear transformation method. So we using, suppose u is a dependent variable zeta and z. So zeta is a function of x plus y minus t is a transformation, and putting into the main original equation. So we see that this equation reduces into the 1 plus 1 partial differential equation. Previously, this equation is 3 plus 1 using this transformation. So this reduces into the 1 plus 1 partial differential equation. So by taking the phase variable phi I in the equation number 5, here pi zeta minus wi. So this is the important role of this phase variable. Here the pi is the real parameters and wi's are the dispersion coefficient. So using this phase variable by this combination, substituting in this equation, so we will get the value of the wi, means the dispersion terms. And using this dispersion terms, we use the another Half-Buff transformation, and here we find the value of u. This is the important task to find the value of this r. The sum of the researcher using directly r, but first we have to find the value of r, and by using this transformation f zeta z is equals to 1 plus e raised to the power phi I in equation number 5. For solving for r, so we will get the value of r 6 by lambda 3. So substituting of this transformation with this r into the equation number 5. So this equation 1 plus 1 equation transform into the bilinear form. So the first task is to reduce into the, after applying the Panay-Levy analysis to check the integrability, the equation transformed into the bilinear equations. And bilinear form in the D operator. So we use the bilinear differential operator to define by the Hirota dx, this form of this operator, and using this operator, so this equation converted bilinear equation, this bilinear equation converted into the Hirota bilinear form. So first we take, because we are talking about the N-Rock wave solutions. So here we see that if we assume the auxiliary function as a generalized form of the Rock wave solution governed by the N soliton. So because our equation is in u and u is a function of zeta and z. So we assume, so this is a auxiliary form of this form. This is the generalized form. Here we see that this alpha and beta is the center control of the wave center, and assuming this, solving and putting this equation into the main equation for the Rock wave of the first order, because this is the summation from k is equals to 0 to n plus 1. So I am first take the first order, the rock wave, so putting n is equals to 1 and solving for the fz is equals to this one. So on substituting the equations 13 with equation number 9, equation number 9, and into the main equations, so we will get the analytic solutions for our rock waves. So this is the first order rock wave solution. Here we see that zeta minus alpha and alpha minus zeta square having this solve. So here, this is the first rock wave of the first rock. So these first two figures showing that this is the with respect to the singularity along the alpha is equals to, this figure is alpha is equals to 5 and beta is equals to 7. And these are the respective contour graphs for the relevant parameter when we're taking lambda 1 is equals to 0.5, lambda 3 is equals to -1, lambda 2 and lambda 4 is equals to 1. The same combination we are taking for n is equals to 2. So we get the rock wave of the second order. So we choose dependent variable function fz, n is equals to 2. So solving this is these assumptions, this auxiliary equation, solving for n is equals to 2. Yeah. So solving this n is equals to 2. So first we find the coefficient to finding the this coefficient q0 and q22 by substituting equation 16 into the bilinear form 19 and equating the coefficient of the distinct power of the zetas and z equals to 0. So we get a system of equations. After solving the system of equations, so we will get the value of these constants. And putting this value of the constant into the main equations in the bilinear form, so we will get the solution of this form. So here, so this graphic showing that it's a beautiful demonstration of the second order or rock wave. So here we see that there are the two rock waves with the singularity for alpha is equals to 7 and beta is equals to 10, and this figure for alpha is equals to 0 and beta is equals to 0. So here the larger rock waves having the leading nature for the other rock waves. So if you are seeing the oceans, so there are the giant waves where we are occur the lumps. So these forms are having the rock waves. Similarly, we are going for n is equals to 3, and this work is not easily by hand and paper to solve. It is a highly computational work. It takes almost 1 and 2 months work by the highly computational work, because we cannot find the final assumptions, because if you see, this is not an analytic solution. It's just simple transformation, putting this value into these equations and to demonstrate these graphics. So if you have to finding the rock waves of third order or the second order on this form of, so that form are occurring. So in this figure, if you see that the one rock, second rock, and the third rock, the larger rock is having the leading nature for the others two rock waves. So the researcher working on the first rock, second order, third, and the fourth rock waves, not for the 5, because the highly computational work is not working here. So the main motive of this research, the first example, first constructing the newly formed nonlinear evaluation equation, which is the combination of the Jimma-Murphy and the KP equations, and to check the integrability, it is integrable, so then we can apply the Hirota bilinear method, and to find the rock wave of the first order and the second order and the third order. Similarly, we have taken as a second equations. This is a highly nonlinear evaluation equation, the mu1, mu2. Here, this term is a dispersion term, ux and uy. And same, when we are choosing mu is equals to 2, mu is equals to 3. So this equation, the main equation, transformed into the Jimma-Murphy equations. And the second one, when we are assuming this form of, so this equation, so this new, the KdV type generalized equation is a combination of a Jimma-Murphy equation and the KP equations, and which were published in this, the applied mathematics and computations. And the second one is the nonlinear dynamics. So first, as we are earlier, we choose The first is the phase variable. So here I'm choosing the psi I is equals to AIX plus BI and CIZ minus DI. So here DI is a dispersion term. I'm finding the value of the dispersion time by putting the mu is equals to e raised to the power psi I into the main equations and finding this value, that this soliton. So, and the next step is the using the auxiliary function, means u is equals to n log f with the derivative of x. So putting this value with the combination of 1 plus e is x, so we find the value of, in the previous example, I'm taking here as capital R, but I'm here is n. So it's up to you. You are choosing capital R or capital N. Okay. And with this combination, so we find the bilinear form using the Hirota bilinear transformation. So this bilinear form into the Hirota bilinear form. So here we are talking about the lump and the hyperbolic cosine function. In the previous example, we are showing that the rock wave of the first order, second order, and the third order. But here in the second example, with the lump and the hyperbolic cosine. So I am choosing it as a trial function eta square, eta 2 square, cos hyperbolic plus b. So the value of eta 1 is equals to v1x plus v2y. It's a combination of x, y, z, and t. Similarly, eta 2 and eta 3. So here the vi, v1, v2 from the v15, we have to find, we have to obtain. And putting this combination of a trial function into the main equation by collecting the coefficient of the independent variable, we get a system of equation in constant vk. By solving the system of equations, so we can find the values of all the vi's. So after solving, so we will get a solution of this form of, this is the analytic solutions. And this is the beautiful graphics of the interaction between the lumps and the hyperbolic cosine waves. So here you see that there are the three kink waves with the interaction between the lumps, and in the second one is the two lumps, and the third one is a 3. So if you have seen this 2D graphics, so they are the 3 kink wave with the lumps. So this is the beautiful representation if you are working on the Oceanio dynamics. So they are the the Hirota method technique, and they are the sum auxiliary equations. In the next example, we are seeing that the interaction between the lumps and the kink solitons. So I am using here, in the previous one, we are choosing the cos hyperbolic form. Yeah, here the cos hyperbolic form. In the second interaction, we are choosing, we are using is the exponential form of terms. So if the same procedure we are follow in the previous one, and this is the analytic solutions, and this is the kink wave with the lumps. So this is the beautiful representation for the interaction lump and the kink soliton when we are choosing the f expression in terms of the exponential terms. Now, so this is the important research. Okay, here the newly obtained solution shows the internal dynamics of the nonlinear system, including the soliton interaction property characteristic and the stability properties of the waveform. And the present results open the several promising directions for the future investigation. So these analytic techniques is also work on the, if you have the variable coefficient nonlinear evaluation or the higher order evaluation equation, that model are the more realistic physical method. So in this time, we are also working on the same topic with the variable coefficients equations, constructions of a new generalized evaluation equation, which is the combination of the existing nonlinear evaluation equation is the KDV equation, KP equation, Jim-Amavi equations, and the other combinations of the nonlinear equations. So this is my research lab. I always acknowledge my research group. It's Ajay, Vinith, Agam, Nikita, and Setu. These already 2 guys done their PhD, and these 4 guys are the newly to join my research group. So I always acknowledge my student to publishing a good work in the highly indexed journals like nonlinear dynamics, computation, and mathematics. So these are the related references for this work. Thank you so much. If you have any questions, you can ask. Because it is not a simple works, because it's a highly computational works, and it is not easy to show the two highly nonlinear evolution equations to present a work in a half an hour. So it is not easy.
Thank you so much, Prof. Are there any questions online?
Yeah, there's one.
Should we do online first? We have a couple of times.
I'm sure surgeon is for
Yeah, if you have any questions here, you ask.
May I ask question?
Yeah.
Actually, can you give definition of integrability that you use? Because there is no exact definition of integrability. I want to know, is it possible?
Yeah, there is no exact definition. First, you apply the Penny-Levy test. So you have to check the resonance terms, which is satisfy the condition of compatibility. If the condition is checked, then you can say that the Penny-Levy test is okay. Because it's depend on your computation work. If you suppose if you have the 3 + 1 dimensional, means they are the 4 variables. So the resonance terms are the 4 integers.
Am I right that if you have, if equation satisfies Penny-Levy condition, then this is integrable equation? Is it right?
Yeah. So first you have to check the resonance terms, the resonance conditions.
Thank you.
I think, Professor, I have a question.
Yeah.
Such a good talk. My question is that about the equation number 4 that you discussed in your slides, where the Lorentz series was discussed. My question is that to approximate their function by using a Lorentz series, is there some mathematical motivation or some physical motivation is there?
So it's a criteria to check the Penny-Levy test. So we need a Lorentz series to check the Penny-Levy test. So we are assuming this is the summation of j plus lambda. So finding the integer number delta, because the main equation is if you have see that x, y, z, and t, they are the 4 independent parameters. Independent variables. So the resonance having the 4 integers. Okay. So if you have, it depends on the highest order singularity on the occur in the main equations. Okay. So if you have the delta is equals to -1, having the singularity is on the highest order. Okay.
So
yeah.
In my understanding, we can also take the basis sets of orthogonal polynomial for the expansion of these functions.
Polynomial.
Yeah, basis sets of orthogonal polynomials.
So it's a criteria. You have to check when we apply the Penny-Levy, how to apply the Penny-Levy, because we have to also check the resonance conditions. No.
Okay.
If you are applying the Penny-Levy test, so if you have condition, if the satisfy all the resonance condition with the compatibility, so it means the Penny-Levy test is checked. Okay. It means the given equation is the considered equation is integrable. So here I am applying the Penny-Levy test to check the integrability of the constructed equation.
Okay, thank you. But which solution space you considered in which your solution will exist, because it's not mentioned there?
No, I am not taking, because it's a highly nonlinear equation, because x, y, z, and t. If you are talking about these equations.
Right. When you do a mathematics, for example, when you do a mathematics of the equation, then you have some functional space for this.
Yeah. It's a variable of 3 + 1. So it's a real and time also positive.
Hi, I have a question with your construction of the in-row wave solutions. So with the bilinear approach, what you can often do is what's called the Soto formalism, which allows you to construct in-wave solutions. You construct the wave solutions in a form of a determinant. Rather similar to what you have in inverse scattering. And I wanted to ask if this is something that you have considered in constructing these.
Can we discuss in the later time? Because I am assuming here is the n soliton auxiliary function in terms of n. So I am showing that the solution rock waves for the order n is equals to 1, n is equals to 2, n is equals to 3. So there is a highly computational work. If you want, then I will see the calculation how to work on it.
Sure.
Yeah.
That's cool. And then the second question, I'm also curious about this Painlev test. So is the Painlev test a necessary or sufficient condition for the applicability of the bilinear method?
Yeah. Suppose if you are taking any equations, if you are constructing any nonlinear evaluation equation, the first question is, this equation is integrable or not? So if you are applying to check whether it is integrable or not, so you can apply the Painlev test. If the Painlev test is checked, so then you can say the considered equation is integrable. Doesn't succeed. Is not. Yeah. If this equation is not work, so we cannot apply the Hirota bilinear transformation method. Yeah. Then we cannot apply the my considered equation, as the bilinear transformation method, Hirota technique. It does fail.
Yeah, so
if it fails, then we cannot apply the Hirota method.
You can't apply the method, doesn't mean it's not integrable. So if it fails, this is where we need Peter Leach.
Yeah, if it fails, so when we can apply
does it mean
then when we cannot apply the Hirota method or Hirota and operator method?
But it may still be integrable. Is it? I don't.
It must be integrable. It must be integrable.
Okay.
Okay, time for one question online.
Well, is the person who has, you can just ask him to speak.
Yeah.
Sajwal, do you want to ask your question? Your hand was up. Good?
No.
I think we need to.
Hello, I have a question.
Yeah.
Can you hear me?
Yes.
Yes. As you mentioned in your talk that the solutions are analytical solutions, and how we can confirm that these are the analytical solutions as we have derived the values for the parameters like eta 1, n1, n2, n3. As this is a very computational method, as we have to perform a lot of computations in these techniques. So how we can confirm by replacing parameters into the original model that these are the analytical solutions?
No, the important thing first, you have to construct the nonlinear evaluation equations first. Okay, and you are asking about in the auxiliary function f, how to change. There are so many methods in the literature. We are assuming the interaction between lum and the king soliton and the lum into the two interactions. So this is already existing method in the literature. So you can find there are so many published paper in the nonlinear dynamics. Okay. Just we have used the transformation, means the auxiliary function form of the solutions, and then apply it. Are you getting the answer?
Okay, it means that if we find the lump solutions for any particular model.
Yeah.
Yes. So we will define that the method works correctly if the graph of the lump solution will be peak. Either it will show peak and positive amplitude or peak negative amplitude.
The positive or the negative amplitude, the lumps having the positive and the negative amplitude. It is not easy to show the graphics of the the kink with the lumps interactions. It is easy to apply the method on the computational bugs, but it is not easy to demonstrate the graphics. It is the important task, the graphics with the interaction between the kink and the lumps. Okay.
Okay, thank you so much.
Thank you so much, Prof. Thank you guys, and those online, thank you for attending. We will start again at 10:40. You guys off the hook, can have a little break. And you guys, if you don't mind, please, we're going to do a photo session quickly. If that's... Yeah, so if everybody can single file way.
Can you lead fully in front? I think that will do it once.
Great. And thank you guys at the back. You've been great. Thank you.
May I check my slides?
1, 2, 1, 2.
Yeah, we can hear. Possible to, I want to use my own. I want to share and take it now.
Just take note that we're still waiting for participants and guests to arrive. We will open our video once ready, and then we'll do a handover to you.
How many times? 5 minutes, 10 minutes?
Probably around 5 minutes.
Okay, thank you.
Or are they? Surinari. But you're gonna have to say that one again.
Surinari.
Can they hear me online?
Yes, we can hear you.
Okay, great. Everyone, please just give us a minute just to get everyone's moving in to settle down. For those that are here, sorry, the people in, we're having a dinner tomorrow night at 6. I'm going to pass it around. Please go right next to your name, put an X if you're not going to attend, and a tick if you are going to attend. Got it? 6 p.m. I think it's going to be at Cameron,
I don't know.
but we're not 100% sure. Oh, just pass it on. And please make it close to your name so we can see. Okay, I think we're going to start. Otherwise, time's going to run a little bit late. So our next presenter is online, Professor Surinari Malesko. Thank you and welcome. He will be speaking to us about applications of equivalence transformations, and he's from Surinari University in Thailand. Thank you so much, Prof.
Thank you very much for introduction. I will start. So first of all, I want to thank the local organizing committee, Professor Sibusiso Moyo and Professor Abdul Kara and Ali Raza. So for giving me opportunity to talk on this conference. Even I am in organizing committee, but I want to say that it is imaginary organizing committee. So my talk will be related with applications of equivalence transformations to group classification. I will explain why it is. I will talk about equivalence transformations. So outline of the talk is the following. First, I will remind somebody to just explain what is equivalence transformation, what is admitted transformation. Then I will talk about the most important part related with classification of equations. This classification is related with group classification. And then I will give 3 examples. If I have time to, it will be 3. If not, then I will give only 2 examples of applications of equivalent transformation. So then first, what is transformation? So this is change of independent variables. Then among such transformations, we say that admitted transformation. What does it mean? It means that if you have equation x, independent variables u, dependent variables p, derivatives with respect to independent variables, and phi is arbitrary element. For example, it is a state equation in gas dynamics, so equations. And then using these transformations, this means that we transform independent variables and dependent variables and derivatives according to this change. And we will substitute this equation, and this is new function. So solution becomes solution of the same equation. Here I want to mention that function phi is still the same. Then it is called admitted transformation. If we do change such that this function can be changeable, like here, then it is equivalence transformation. This is difference between admitted transformation and equivalence transformation. Equivalence transformation, it means the solution is transformed to another solution, but arbitrary element phi we call arbitrary element can be changed. So this is equivalence transformation. And to find admitted transformation or equivalence transformation, just use this definition. It's too complicated. Then in this case, we use Lie group. So Lie group of transformation. So what does it mean? It means that there is transformation. Here we have parameter, and this is a set of transformations with parameter A. And these transformations are such that if you have A is equal to 0, so this is identical transformation. If you transform with parameter A and then followed transformation with parameter B, then composition it will be the same as transformation with parameter A plus B. Then this it will be Lie group of transformation. So this is short definition of Lie group. Then in this case, we use a whole set of such kind of transformation. So then the same as before, it is admitted if it is transformed solution into a solution, function phi is not changeable. So parameters here, so in function phi can be changeable, of course. And then one more time, it's complicated to use this nonlinear object. Then it is reduced to consider linear object. And linear object is a set of transformations. We consider infinitesimal derivative related with this group, which is linear. So then coefficients of this derivative are defined as follows. Then coefficient related with derivatives because we need to apply for equation. It is easily constructed. It is called combination formula. So then equation which are called determinant equation for finding such kind of coefficient or derivative, they are reduced to overdetermined system of linear equation for coefficient c and eta. So then it is easier to solve than original previous one I told that about Notley group. For equivalence group, it is similar. So we have this formation, we have parameter, we have Lie group, and then this Lie group, instead of calculated nonlinear object, we reduce to study non-linear object. Actually, there is one correspondence between non-linear object and linear object. And here, prolongation formula comparing with independent and dependent variables, it is different because these functions, they are working in different space. For example, function phi, it works in space where it depends on x and u. So then prolongations are different comparing with independent and dependent variables. So then, similar like for admitted, we apply this generator and consider that equations for function c and zeta. So now we have more functions. So then it is instead of studying general formations, we consider equivalent. We consider transformations linear objects, so linear object generators. So the question is why it is necessary to study equivalence instead of admitted, because equivalence transformations, it is easier to find. So experience shows that it is much easier. And then in this case, we have, when I talked about group classification, so then group classification, it is equivalence transformation divide a given system of differential equations instead into distinct classes are related with different elements. So the group classification problem consists in determining these classes, and for a single representative of each class, we need to find admittedly group. So for each representative of this class. So the classification approach to group classification is based on the finding all solutions of determinant equations. So and this process actually to solve these equations, it depends on arbitrary elements, and it leads to studying many cases, and sometimes it is very complicated and even impossible. There are some systems that are impossible to find. At the same time, to find equivalent transformations, it is much easier. So then, for example, here it is admitted transformation, and here we have to solve this for different cases of arbitrary element. We have to solve these equations, many cases, and this is using for finding equivalence transformation. We have to solve something similar, but much easier, because here we have to consider also properties of arbitrary element. Actually, relations between group classification and with equivalence transformations, maybe firstly it was considered by Ibrahimov. He suggested to study equivalence group and to find optimal system of this group, and then using this optimal system to find elements of arbitrary elements. So, and then it gives us group classification, but not complete. So it is, for this reason, it is called preliminary group classification. And these arbitrary elements they found from finding, if we find optimal system, we find some algebras, and for each sub-algebras you need to find one representative, and then for this representative you find invariant, and it gives you this element that we will study. So then question is, it was preliminary group classification, but we need complete group classification. So then how to get complete group classification? And recently, in 2012, Professor Chirkunov, he suggested to consider so-called generalized equivalence transformations. Actually, it is necessary to solve something similar determinant equations, except that these equations are not split with respect to geometrical derivatives related with arbitrary elements. So, and then this way, if you can find generalized equivalence transformations, and part of this generalized of these transformations, of course, it will be equivalent group that I told before. So, and now I will show some examples. So first example, for example, it is dynamic equations for dissociating gas in special dimensions. We had before, we had for one-dimensional case, but here I will talk about two-dimensional. And this is row one. So we have mixture of two gases. One gas is related with rho one, density rho one, and another gas rho two. Then we have the general velocity, and we have temperature, and then we have state equation. For the state equation comparing with gas dynamics, we have a little bit different. I will explain later what does it mean compare. And we have interaction between two gases. So this is function W here, which gives you formation of rate of components, formation rate of components. So because we got used to before to work with gas dynamic equations, these equations also can be reduced to similar system of equations. So this is system of similar system of equations, in particular if W is equal to 0 and concentration, we call this concentration C, is equal to 0, for example, then it is nothing as gas dynamic equations. Here, W is arbitrary element which we don't know yet. So, and we want to classify this equation with respect to function W. So, and in one-dimensional case, I try to solve admittedly group in this case, but it was very, very complicated. And I think that I did not finish because I started applying equivalence group, which is much easier. So you can see it here. So for equivalence group, we have the function W. It is doesn't depend on space variables x and y. Actually, here I also omitted. And time, and does not depend on velocity, so it depends only density, concentration, and entropy. So then, generator in this case, it has the following form. So here we can see that the coefficient of generator related with independent variables and dependent variables depends only on them, and coefficient related with arbitrary element, which is W, it depends also on this element, so W. So then, in this case, it is easier to construct to solve determinant equations for generalized equivalent formations because they are absent. And this is absent because here polytropic gas, or for polytropic gas, even for gas dynamics equations, Kunovsky gave example that it corresponds only equivalence groups. So then this means that now if I find equivalence, it gives immediately me and classify it, and it gives me complete group classification. So then this trivial calculations, it gives that admitted generators, equivalent formations, equivalent generators, they can consist of the following: this then two Galilean, then this is one rotation, this is shift with respect to time, this is related with polytropic gas, so, and then it is two scaling. So then we can construct after that optimal system. Optimal system is based on the commutator table. So actually we need to construct, we need to find commutator table, then using commutator table, we can find so-called inner automorphisms. and inner automorphisms are used in order to simplify generators. Actually, here I forgot to say that here numeration is unusual, so because it is x1, x2, and then x3, x4. So I use the same notation like it is in applied in gas dynamics. So then, in this case, optimal system it will be algebra. So for this generator, we can see that it consists only for changing W function. So we need only that it will be changed rho, C and S. So it is only this last generator, 7, 8, and 9. So then we can do projection of the generator on space where function W depends on, and then it will be only these three generators. And then it is easier to classify this algebra. So then it consists, optimal system consists of the following algebras. But if you have generator P7 alone, then you can see that here it doesn't work for finding function W. Then this means that we have only three choices. So these three choices we can use for finding function W. So we need to find invariants for this, and so this is example. So for example, for this subalgebra, we have the function f it is the following. So W it is unknown. Now we apply a generator to this and consider the manifold defined by this one. So it is like equivalence, like admitted generator. So and then we will get this equation, and we can find general solution of this equation. So similar we can do for other choices. So two other choices, and then this way we have preliminary group classification, but this preliminary group classification coincides with complete group classification. So we have three choices. We have the function W has the following form, where function G, argument of this function G has the following representation, and the admitted generators for each case are such that generators up to x1 up to x6, they compose kernel. Kernel, it means that they are admitted for any case, so for any function W. And except kernel, there is one more generator, for example, for first two elements, and for third one, we have two additional admitted generators. So actually, this one, we have projection because we cut part related with W. So W, it will be invariant, and we cut it from generators which are given here. So by this way, we obtained for complete group classification. Actually, we get group classification for one-dimensional case, and it is interesting that this is the same group classification. So function W, representation of function W is similar as for one-dimensional case. And even more, we consider stationary equations that I explained in Euler coordinates. Then similar, we can get result with Lagrangian coordinates. Similar to the stationary equations, but in Euler coordinates, so all dependent variables, they don't depend on time. And similar, we have for such kind of equations, we have stationary solutions, which is stationary in Euler coordinates. So we reduce them to Lagrangian coordinates, and similar, we have the same representation of arbitrary function W. So then here I want to show it. This is just how to reduce to Lagrangian coordinates because time is going very fast. So then here I will give one class of solutions. So then first we have the following partially invariant solutions. So for partially invariant solutions, we choose the following subalgebra, which consists of two shifts with respect to x and y, and two Galilean transformations. Actually, in this case, invariant is not enough to find invariant solution. So then, part related to part invariant consists of the following: rho is rho c and entropy. They depend only on time t. and superfluous functions u and v. So they are arbitrary functions of t, x, y. After substituting an equation, we will get that we have a system of ordinary differential equations. Here, function t depends on time, and system of overdetermined system of equations. So then, in this overdetermined system of equations, we have two variables, u and v, and t is actually it is related with rho. So, question is first, what about compatibility? So, compatibility, this system is not innovative. We need to system will be not active, and so it is interesting that it's possible to find functions here, but in variables u and v, it is complicated. Then it is possible to introduce something similar to prime function, and it is possible to reduce to system which is involutive, and then it is possible to show that function p has to satisfy the following second order ordinary differential equation. And how I found that this change of variables, it allows to get a general solution of this equation. So, and here we have three arbitrary constants. So, and this class, here I want to mention a little bit, not about group classification. I want to mention only something that in the seminal work of Patera Winters, we found that if you want to use these equations for finding optimal system, then one of first steps, which is this method was proposed by Professor Ovsyannikov, two-step algorithm. So, which consists of construction of ideal and then subalgebra, and then first to classify subalgebra, and then to add to join with ideal. For example, here it is the following subalgebra, so three-dimensional, and this subalgebra is absent in a very well-known paper of Patera and Winters in 77. So this is unfortunately, so otherwise I could reply. So this type of solution, it gave ideas and generalized it. So for example, before it was rho, t, and s, it was function on t. Then assume that it also depends on x. Actually, it's interesting that it is possible to find in this case also solution. And in this case, if ui is not equal to 0, it is reduced to the previous case to partially invariant solution that I told before. And if ui is equal to 0, function v is split in these two parts. And very important that here function v1 and v0 depends only on tx. And all other functions, so u, because of ui is equal to 0, it also depends on tx. And then it is split in two parts. So, and this system of equations is something similar to gas dynamics, except this equation for function v1. And v1 is involved here. It means it's something like source in this case. So then it's possible to find admitted equivalence transformation to do group classification. Group classification is the same as in previous case. I won't talk about this. We decided to have to check, because before we used for Arrhenius function, Arrhenius range function, we constructed a solution of strong explosion problem. So we decided that it is possible here to use this solution. So it is because here it looks like in previous case I needed for the problem of strong solution, so strong explosion problem solution, except this equation. So then we try to apply this to such kind of problem. And it is interesting that here we have one generator, which is nothing else as scaling. So and we can use representation of solution for this scaling. And then this is similar to solutions which are used for strong explosion problem. Actually, not completely, because in classical it is a little bit different because it is considered not x over t, it is considered x over t to the power 2, but it is for gas dynamics, it exists, so such kind of some similar solution. So then we applied this for solving strong explosion problem. And what we obtained here, we have, for example, here it is a case where it's clear, so this is gas dynamics when function v1 is equal to 0. So, and this is case, this is velocity, so velocity u. And then this is case when we have that this is initial value for function v1 is positive. So then it is this one. When it is negative, it is this one. Here similar for density. So this is representation of density. This representation, it is between them, it is for gas dynamics, for classical gas dynamics. And this is the temperature. And this is a velocity v1. So this is for positive, and this is for negative initial data. So, and so this is the first part, the first example that I wanted to talk. Next example is related with interesting problem. So I was involved in this problem recently. That 1 year ago, Professor Pukhachov, he invited me to collaborate on the following problem. So this is, we have early equations. So early equations, this is implicit incompressible fluid dynamics equation. So here U is velocity, rho is density constant, P is pressure. So that question was proposed by Gromyko in 1881. He suggested to start considering solutions which are such that rotor of velocity is collinear to velocity. Later, in 8 years, it was proposed independently by Beltrami. Actually, now in English literature, it is called Beltrami flows, but in reality, Gromyko was first. So then it was also applied to the Navier-Stokes equation, for example, Steklov. We have Institute of Mathematics in Moscow, which is called Steklov Institute of Mathematics. So then he also tried to find some solutions in this case, and then it was repeated later by Pascal. Here I want to mention about one book. Unfortunately, it is a lesson where it is given very interesting review of up to this year. Actually, later it was also some publications, but I won't talk about this because I have no time. So then, in this case, what we try to construct some functions alpha. So here, assume that this function depends on x, y, and z. If this function depends on time, so unfortunately, right now I don't know a solution what happens. But if it depends on the independent variable, so then these equations are reduced to the following overdetermined system of equations. And question is the following: that if alpha is given, and what is this system? Because this is overdetermined system. Is it involutive? No, it is not. I don't know answer. So that, but for case if alpha is constant, it was considered by Gromyko. You know that it is Gromyko form of fluid dynamics equation. So it is the same person. And if it is constant,
I have to interrupt you. Just letting you know you have 5 minutes left.
okay, I try to finish it. Thank you. So, and in this case, if alpha is constant, it was the system involutive. But in case if alpha is not constant, then Gromyko, he wrote, integrating these equations in general presents difficulties that I have not been able to overcome. So using group analysis, we overcame for several cases. So then first case, of course, find equivalence group. So we did not find generalized transformations, generalized equivalence transformations, but we tried to find equivalence group. So actually, if you try to find equivalence group, you need to have the system must be involutive. But here, system is not involutive. But then we had the following peak. We assume that alpha is a dependent variable among u, v, and w. In this case, system becomes involutive, and we can find admittedly group, including, so we consider that alpha is dependent variable. So we can find admittedly group, but this is not admittedly group for original problem if alpha we think that it is given. So this is equivalence group. So then this transformations we can consider as equivalence transformations. So, and then we can use the same steps to study optimal system of this algebra, and then for each element of this algebra, so we can construct representation of function alpha, and then we can use we can find we can find solutions, and we can say that in this case the system is involutive. So then this optimal system is trivial to construct because it is given already by Professor Ovsyannikov in 1994 when it was studied 11-dimensionally algebra. So and then in this, after when we used this optimal system, we can construct arbitrary elements. So this is alpha, and then this is admitted generators so among also kernel. So kernel additional generators, and for example, solution. So this is example of solution, and when we have alpha is a function of radius. So then radius can be cylindrical coordinates and in spherical coordinates. For example, in cylindrical coordinates, so then it is possible to find solution. It has the following form. So function f is arbitrary, but we need to find this function derivatives for vz. We need to solve it the following second order differential equations. It is interesting that in particular case, when it is k over r, so then if this equation becomes Euler equation, and we can find general solution which depends on this constant q. So in spherical coordinates, it is similar. We can find the solution and reduction. So then in this case, it is functions beta 1 and beta 2, but they depend on phi and theta. I'm sorry, and this is Cauchy-Riemann equation. So for Cauchy-Riemann, we have general solution. So this means that in this case also we can guarantee so that system is involutive and function f is arbitrary. So then here I want to mention a little bit the following, that this method of preliminary group classification can be applied not only for differential equations, but also for differential equations, which we applied. So this is for Fourier transformation of the Boltzmann equation. So and if the function is equal to 0, we can find admittedly algebra. Then we use this admittedly algebra to find to use this as equivalence transformations. Actually, for such kind of equation, when g is equal to 0, there is only one solution for the Boltzmann equation, explicit solution. It is one of them, of course, it is Maxwell solution, but in the Maxwell solution, this is integral is equal to 0. So when it is not equal to 0, it was constructed first to Bobolev, and then it was repeated by Crook and Wu. So then the question is it possible to construct more general case of equivalence transformation? So then in 1984, Spiga, he constructed solution for the Boltzmann equation with source function which is not equal to 0. So this is in our case, I can represent it this form. So and then but later, Santos and Bray, they showed that it is possible to reduce solution that he constructed, Spiga constructed. It is possible to reduce to the solution which is called Bobolev-Crook-Wu solution. So then we used also this transformation. So then we studied it. We also found source function using preliminary group classification. So this means that here I wanted to mention that this is possible to apply not only for differential equations, but also for differential equations. So then this work was partly supported by Russian Science Foundation with this number. So then here, this is some publications which I used. Not all, this is just some points. And thank you very much for your attention. I finished exactly in time.
Thank you so much, Prof. That was right on target. Unfortunately, we don't have time for any questions. So if anyone has any questions, please will you direct them straight to the Prof. Next up, we also have somebody online joining us, Professor Rayad Ghanem, all the way from Qatar, the University of Virginia Commonwealth University, which he joined in 2014 following an extensive career in teaching in the USA. Okay. Okay. Any questions online? I think maybe the connection was. Okay, I'll go ahead. Ali, good. Happy to go ahead. Okay, great. Thank you so much, Prof. Rayad Ghanem. He also served 2 years under a NASA-funded grant, which was teaching teachers how to teach math and science to younger students, which I think is a very valuable 2 years spent. Thank you so much, Prof. Over to you.
Thank you so much. I really appreciate it. Can you confirm you guys hear me?
Yes.
Yes.
Good, good. Thank you so much. Let me share my screen. Sorry, one more question. Can you confirm you see my slides, please?
Yes, yes. All good.
Well, thank you very much. I really, really appreciate it. And I wish I was able to be in person with you guys. But as I promised Dr. Ali, inshallah, next time I'll try my utmost best to be with you. So I have decided to give a general talk about symmetries of differential equations, Lie algebras, and talk a little bit about the project that I proposed in my abstract. So for those who are experts in the field, I do apologize in advance if most of what you see is elementary, but I really wanted this to be kind of elementary, entertaining talk as well. So let's start with what is symmetry. So symmetry is, it's a transformation that leaves an object unchanged or invariant. So for example, look at this equilateral triangle and the angles, I named them 1, 2, 3. So if you rotate by 120 degrees along any one of these lines, then you will find that triangle is unchanged. So rotation by 120 degrees, by 240, 360, bring it back, you will not notice that these triangles that have been rotated. So rotation by 120 degrees is a symmetry, 240 is a symmetry, 360 is a symmetry as well. The other thing is, what is it? Sorry, here I mean reflection, here rotation. So let's look at this circle. Pick a point here, XY on the circle with the angle theta. If I add an epsilon to my angle theta, then my coordinate will change. The order pair will change to X bar, Y bar. And then here what I did is I write in polar coordinates X and Y. So X equals R cosine theta, Y equals R sine theta. And so X bar would be, in terms of the new angle, which is theta plus epsilon, is R equals cosine theta plus epsilon, R equals Y bar equals R sine theta plus epsilon. So what I want to do is eliminate theta. And so after I do that, I get X bar written in terms of X and epsilon, X and Y and epsilon, and Y bar equals, is also written in terms of Y and epsilon. But We know the equation of the circle is x squared plus y squared equals to r squared. But if I also square the x bar and the y bar, I will end up with the same thing. It's x bar squared plus y bar squared equals to r squared. So the equation is unchanged. So if I go back here, I will find out this transformation, the x bar, y bar, did not change anything. So here we have that transformation is a symmetry. Let's look at a much more complicated equation, such as this curve, x squared times y squared minus xy squared plus 2xy minus y squared minus y plus 1 equals to 0. This is invariant under the following transformation. So if you take x bar to equal to x plus epsilon, y bar equals y over 1 minus epsilon. If you solve for x and y and plug in everything, simplify, you might need to use maple, you will end up with the very same equation, except for every x you will see x bar, for every y you will find y bar, which is the same curve essentially. And so this equation is unchanged under this transformation, and so this transformation is symmetry. Let's consider the following transformation, just scaling. So x bar is a times x. So we know that an element is in the above set is a transformation of the form phi sub a of x is ax. Then we will find out, this is a simple exercise in abstract algebra. So the set of all these transformations is closed, it's associative, it has an identity, and not only that, it has an inverse as well. So it does form a group in the abstract group definition. But if we reparameterize the group by taking A to be e to the epsilon, then the transformation is going to be smooth in terms of x and analytic. So you could differentiate with respect to x, and you could write the Taylor series expansion in terms of epsilon. And when you take epsilon equals to 0, e to the 0 is 1, which means you're just scaling by 1. So every x stays x. So basically, it's unchanged. So in this case, we have what's called a Lie group. So a Lie group is what? In a simple language, it's just a group, but with a differentiable structure. Let's look at this example, a bit more complicated. X bar equals xy over y minus epsilon, y bar equals y minus epsilon. If we consider this transformation, we can show this is a group under the law of composition, but also we can show that it is a Lie group. So consider the following. So this is the definition of a Lie group. X bar equals f of xj epsilon. So you have a set of transformation. This will be called a Lie group. If it's a group, but your f's, these functions, these transformations are smooth in x, meaning you could differentiate, and also they are analytic in terms of epsilon. You could write the Taylor series expansion. Now, when you take epsilon equals to 0, then you will find that we have the identity transformation. So who is Lie? Sophus Lie is a Norwegian mathematician from 1842 to 1899. This is a picture actually of me. I attended a workshop in Norway many, many years ago. And this is actually his house in the North Forest. And I'm one of these groups. So quick comments about him. He was a professor in Christiania. Now it's Oslo. Lie attended lectures by Silo, as in Silo theorem. He paid a visit to Felix. Felix and Lie published a paper in 1871. Lie conceived the idea of finding an analog of Galois theory for differential equations. So one of his greatest achievements was the discovery that continuous transformation groups, now called Lie groups, could be better understood by linearizing them and studying the corresponding generating vector fields. All right, the generators are subject to linearized version of the group law, now called the commutator brackets, and have the structure of what today called Lie algebra. So what was actually Lie's idea? What led him to this discovery? This is what he did. Suppose we have an ODE or PDE. Then can we find a change of variable or change of variables to make this ODE simple, like separable equation? Let's look at this example. So consider the following differential equation. dy by dx equals y squared minus y over x minus 1 over x squared. If we consider this change of transformation, which is x equals e to the s, y equals r times e to the s. So basically x and y are functions of new variables r and s. Then we could rewrite this ODE in terms of the new variables s and r, and we obtain ds by dr is 1 over r squared minus 1. So this is a separable ODE. We can solve it. We find s, and then we could just solve for y. Let's look at another example. dy by dx equals y over x plus x squared over x plus y. Then if we choose this transformation, so x is a function in r and s, which is here x equals to s, and y equals r times s, we could rewrite this differential equation in terms of r and s as dy by ds by dr as equals r plus 1, which is separable differential equation. We could solve it for s and then eventually solve for y. Let's look at a much more complicated one. This one. I'm not going to read it for time's sake, but if we take this transformation, we get x equals 1. If we take this transformation, x equals 1 over r plus s, y equals 1 over s, we have this differential equation, which is separable as well. So there are two questions based on the examples that I presented. How do these ODEs, I presented 3 examples to you. What do these ODEs have in common, and how did I pick these transformations? So that was Lee's idea. Answer for question 1, they're all invariant under some Lie group. So we got to talk about this. And the other question is, let's talk about it later. So let me summarize what I did. I presented 3 equations. I presented these transformations, but moreover, these 3 are invariant under these Lie groups. What does that mean? Here, the transformation x bar equals e to the epsilon x, y bar equals e to the minus epsilon x. This set of transformations form a Lie group. So if I use the chain rule, like something we teach in calculus 1, if I rewrite dy by, if I substitute this in this differential equation and using the chain rule, I'm going to find dy bar by dx bar equals y bar squared. So basically, this does not change my ODE. So it's invariant. Similarly here for the second one and the third one. So how do we find what's called symmetries, point symmetries, or infinitesimal symmetries of these ODEs in general? So we start with, what we're looking for is a transformation x bar equals f of xy epsilon, y bar equals g of xy epsilon. So it's one parameter group. With what I want, if you remember, with the definition of Lie group, when I take epsilon equals to 0, I get the identity transformation, means x bar equals to x, y bar equals to y. So in math, as you know, you're all mathematicians, whenever we face something complicated, we try to make it easy by linearize it. And so here exactly that's the idea. We linearize this transformation, so using Taylor series expansion at 0. So x bar equals f of xy 0 plus the partial derivative of f with respect to epsilon at epsilon equals 0 times epsilon plus an error of order 2. Similarly here. So if you look at this equation, I know this term is just x. So all I need to find is this term and this term. So this is what I need to do. If I do so, then I have my transformation. So we simply write them as x bar equals x plus big X of xy, and y bar equals y plus big Y of xy. So these are the infinitesimal symmetries of my differential equation, and these are unknown, and I need to find them. So how do you find them? Well, before I do that, let me give an example. So given this Lie group, then from the Lie group, I can easily calculate the symmetries. What I do is just differentiate this with respect to epsilon and take epsilon equals to 0. If I do in this example, I get big X equals to X. If I do it here, differentiate this with respect to epsilon, take epsilon equals to 0, I get big Y equals to negative Y. Now, Lie came up with the condition for which we are able to find these big X's and big Y's, and this is what we call Lie invariance condition. So let's look at first order differential equation. So big dy by dx equals f of xy. Then these are our infinitesimal symmetries. So if we use the chain rule and simplify, these two are going to be infinitesimal symmetries if this condition is satisfied. And this is what's called Lie invariance condition. And so as you see, you will end up with a system of partial differential equations, and you need to solve it. So to better understand this system, to better code it, and later on, if we have higher order, we use this notation. So we use this vector field gamma equals x partial x plus y partial y. So basically what we're saying, we encode our symmetries in terms of vector fields. This is the first prolongation of this vector field, and then Lie invariance condition becomes, this is going to be a symmetry if the first prolongation applied to del equals to 0, where del is this function. And so it simplifies to being this in terms of this notation. So in general, if you have nth order, this will be the Lie invariance condition, and you go on. So I did talk so far about the idea of Lie groups, and this is how it came from Lie. So what is a Lie algebra here? This is the definition of a Lie algebra. So basically you end up with a vector space, but with an extra operation, which we call the bracket operation. So the bracket operation satisfies conditions, 3 conditions. Number 1 is the skew symmetry. If you take any 2 elements in your vector field, and you take the bracket and you switch, it's skew symmetry. So it's bilinear, and also it satisfies Jacobi identity as well. So Jacobi identity is, sometimes we think about it as being associative in terms of geometry. And the simplest or main example to think about when it comes to Lie algebras is the group, the space of all n by n matrices. Well, here it's a vector space, right? But moreover, we take the bracket, the extra operation, to be the commutator. So if you take the commutator of AB, we define it it is AB minus BA, and we know this is not by default 0. They don't necessarily commute, and it satisfies all conditions. Moreover, actually, we have a bigger theory, which is if you have any finite dimensional Lie algebra, we can always think of it as a subspace of G, L, and R. So it's an isomorphic to subalgebra of G and R. This is a problem that me and my collaborators worked on it for many years, which is, given any n-dimensional Lie algebra, abstract Lie algebra, could you find or a representation of that Lie algebra in terms of matrices? So we did work on that. We worked on even minimal representation of matrices. Examples of Lie algebra: the space of all skew symmetric matrices, the space of all trace-free matrices, and skew Hermitian matrices that are very well known Lie algebras. Let me give other examples of Lie. People worked on classifications of Lie algebras. So for example, here, this is a 3-dimensional Lie algebra, and the convention is we give the non-zero brackets of the Lie algebra. So the basis here is E1, E2, 3, and in principle, you should have 3 parentheses, 3 brackets, but we don't list them because they are 0. So E1 with E2 is E3, and then E2 with E1 is negative, E3 we're not going to give it, and E2 with E3 is 0. And the other ones, E1 with E1 is 0 by default because of the skew symmetry. This is another Lie algebra, 3-dimensional Lie algebra. These are the non-zeros. This is 5-dimensional. This is another 5. These are 5-dimensional. Here, for example, the last 2 examples, or this example 5, 7, you will find a parameter A, another parameter C. So actually, it's a family of Lie algebras. So here, one more thing I want to point out, why this is called 3-1. This is 3-9, 5-1, 5-7. So as I said, people worked on classifications of low-dimensional Lie algebras. So we know all 3-dimensional Lie algebras up to an isomorphism. So this is the first one, 3.1, indecomposable 3-dimensional Lie algebra. This is the 9 in the list. This, we know all low-dimensional 5-dimensional Lie algebras. So we have, for example, 40 indecomposable solvable Lie algebras. This is the first one in the list. This is the 7. This is the 12. The 12th in the list. All right. Now we have simple Lie algebras. So simple Lie algebras, skew multiplication or bracket. Okay. So The skew multiplication or bracket gives a Lie algebra, and then okay, as such, one may speak of subalgebras and ideals. By analog, we finite, we call Lie algebra simple. So we call a Lie algebra simple if it's not abelian, if it has no proper trivial ideals. We recall that Lie attended Silo's lectures in 1863. Already by 1890, Killing tackled the problem of classifying simple Lie algebras. So simple Lie algebras, AN, the special linear group, BN odd orthogonal, CN, DN, the symplectic, the even orthogonal plus 5 exceptional Lie algebras. G2, it's of dimension 14, a 4 dimension 52, E6 dimension of 78, E7, A8 dimension of 254. Some interesting history. So Killing's big discovery. So Killing was one of the first mathematicians to attempt a full classification of complex simple Lie algebras. His work was revolutionary. He introduced roots, Cartan subalgebras, and the earliest version of Dynkin diagrams. He identified all classical Lie algebras and discovered the exceptional ones, G2, G4, E6, E7, E8. However, and this is important, his proofs, especially concerning the structure of non-simple and semi-simple Lie algebras, were not rigorous by modern standard. Many arguments depended on unproven assumptions or incomplete reasoning. Then Cartan is the mathematician who completed the and perfected Killing's vision. In 1984 thesis, he provided the first fully rigorous classification of complex simple Lie algebras, a complete treatment of root systems and Cartan subalgebras, corrected and justified all steps that Killing had left unproven, a clear description of semi-simple Lie algebras, and direct sums of simple ones. Now, Cartan wrote, and honestly, I don't read French. I can't read French, but I did quote this. So this is what he wrote in his dissertation in French, but I put this in Google Translation, and it says the following. Unfortunately, Killing's research lacks rigor, and in particular with regard to the groups which are not simple. It makes use of theorem that does not prove that does not prove in its generality. However, we have another figure in Lie algebras or in Lie groups, Helgason, born in 1927. One of the major figures in Lie groups, symmetric spaces and representation theory. He wrote the following. It's not usually a credible accomplishment to give a wrong proof of a theorem, which has generally been suspected for some time. But when an incomplete proof leads to a surprise on the level of Killing's discovery of the exceptional Lie group, tolerance is called for. More tolerance is called for. So, quick history about the low-dimensional Lie algebras. So, Olaf in 1891, he classified the nilpotent low algebra over the complex numbers in dimensions less than or equal to 6. Some of them were redundant. Cartan in 1894 classified the semi-simple ones. Morozov in 1958 classified the 6-dimensional nilpotent Lie algebras, approximately 24 non-isomorphic Lie algebras. Mubarak Zayanov in 1963, he classified the solvable Lie algebras in dimension less than or equal to 5. There are 40 families. All right. Zayanov also classified the 6-dimensional solvable Lie algebras with codimension 1 nil radical. We have 99 families. In 1988, Risky classified the 6-dimensional solvable Lie algebras with codimension 2 nil radical. There are 40 families. We have the following theorem. The codimension of the nil radical is always less than or equal to half the dimension of the Lie algebra, which means the 6-dimensional solvable Lie algebra with codimension 3 are decomposable. That's why we don't worry about their classification. Craig Seeley in 1993 classified the 7-dimensional nilpotent Lie algebras and they're over the complex numbers, and there are 130 families. 1998, Gong classified the 7-dimensional nilpotent Lie algebras and they are over the reals, and there are 155 families. Now, I'm going to skip for the sake of time. There are kinds of Lie algebras, like they have the solvable Lie algebras, and in simple language, we think of them, they are, in terms of matrices, upper triangular matrices. This is a simple example. Nilpotent Lie algebras, strictly upper triangular matrices, and this is another example. Lots of applications for Lie algebras in quantum mechanics, general relativity, grand unification, string theory. Now, this is where I want to get to. So on Lie algebra, there's what we call the canonical connection on Lie groups, for which on left invariant vector fields x and y, the canonical symmetric connection.
Sorry,
on
Prof.
Yes.
Sorry, Prof. Sorry to interrupt you. You have 5 more minutes.
5 more minutes?
Sorry.
Okay. Well, on left invariant vector fields, we define the we define the connection as the covariant derivative y in the direction of x to be half the bracket. And then we extend it to any vector field using Leibniz rule. So the goal here is we analyze the symmetry algebra for a very special system of ODEs on Lie groups, the geodesic equations on Lie groups. So how do you find the system? This is how the geodesics are written. So what we need is to find the gammas, to find the system of these, the system of the ODEs, but we do it by computing the covariant derivatives. And we focus on the codimension 1 abelian nil radical Lie groups. So here we calculate the geodesic equations for an n-dimensional Lie algebra with codimension 1 abelian nil radical. So the system will look like this. So as you see, x double dot I is aij x dot jw. So you will find the w, and this corresponds to the codimension 1, and the last one is always 0. So we construct the Lie variance condition, and we will construct the system of PDEs and try to solve this system as much as we can. So we have the following theorem. We have a standard form for this special Lie algebra, the codimension 1 abelian nil radical. We also have a vector field representation, which will help us find the covariant, which will help us find the geodesic equations, which are written in this form. Now, the way we do it, we encode the geodesics through this vector field. And this is the general symmetry. It will be a symmetry to that system of differential equation if the bracket of the prolongation of this with the vector field which has the geodesics encoded is a multiple of the geodesic equations, and we end up with this. I'm going to skip this. So we define pi equals this, and this is the prolongation. This is the time derivative of this, and we construct this system of PDEs, and we try to substitute whatever we know about the geodesic equations, and we end up with this system. I'm going to skip the details for the sake of time and show you what exactly we're looking for. And we try to solve as much as we can. And basically, these are the solutions, the conditions. We end up with this theorem. In the case, so in this case, for the 5-dimensional, sorry, for the n-dimensional with codimension 1 abelian nil radical, so the matrix A, which is the coefficient of the geodesic equations, the numbers in front, or the functions, numbers or function depends, is going to be, in the case when it's non-singular and has trace non-zero, the dimension of the Lie symmetry algebra of the geodesic equations is at least 3n plus 1, and where n is the dimension of the Lie algebra, and at most is, so we have an inequality n squared plus 2n plus 4. Moreover, it's 3n plus 4 occurs when n is non-derogatory matrix, and n squared plus n plus f and only fa is non-zero multiple of the identity. Simple example, for example, if you take a 4-dimensional, this is going to be the symmetries. In fact, it is a semi-direct product of R4 with the Heisenberg direct sum R4. We did the codimension 2 abelian nil radical, and I was hoping to show you some calculation about if you have n-dimensional Lie algebra with r-dimensional nil radical. But before I finish, I want to say one comment. Why are we interested in calculating these symmetries? For 2 reasons. Yes, Maple could do this, but we wrote our own codes to do it. And the main thing is not just to find the symmetries per se, but we are looking at classifications of Lie algebras. And usually these symmetries produce large Lie algebras of dimensions 15, 17, 22, 23, and so on. And we would like to look at these Lie algebras. We would like to look at invariant metrics on these Lie algebras. So it's not just the symmetry itself, but also to find interesting things about these Lie algebras. Well, thank you very much for the opportunity to present. As I mentioned earlier, I want this to be a general talk with some flavor about what we do with these Lie algebras, and I really appreciate it. I unfortunately I need to run to go to teach a class, but I could take a question of two quickly if there is any. Thank you very much. Really appreciate your time.
Thank you so much, Prof. Do we have any questions online? Come on, guys, 1 or 2 questions. Ali, throw a question. No, you got a question? Do you have a question?
Okay.
No?
Hello, Riyadh, can you hear me?
Yes, yes. Is that Dr.
So
Abdul
a quick question. Yes. So can I ask you, did you apply this?
Go ahead, please.
Okay. So have you applied this on standard manifolds like your Schwarzschild or Minkowski manifolds and so on? So in applying your geodesic equations that come from relativity?
No, I have not. I only looked at the canonical connection on solvability.
Oh, okay, thank you.
You're welcome.
Here's a question from...
Hello, Professor. Professor, you are talking about the Killing's forms. And Killing's forms is not good for the researcher. You are talking about in these presentations.
I'm not talking about the killing form. I'm not talking about the killing form at all. This is not the killing
because
form.
most of the researcher to finding an optimal system by killing forms.
I did not talk about the killing form. I did not talk about the optimal system.
Okay.
Sounds good.
Thank you.
But if you want to talk about killing form, let me tell you what we can do and what I'm currently doing with killing form. You know.
I'm interested.
Yes,
Yes,
but
you
I don't know. I'm going to be honest with you. I did not like the comment saying when you said it's not good for research about talking about killing form. There's a lot you can do with killing forms. For example, look at these all these low dimensional Lie algebras. Look at left invariant metrics on these. And you know what? I challenge, find a basis for the killing form. Find all of them.
Thank you so much.
Let me take another question.
May I ask you one more question?
Yeah, please.
I wanted to ask, as I understood from your presentation, that complete study is done for 6-dimensional. What is maximum dimensional algebras were completely studied? I mean, optimal systems, because for 4-dimensional it is given, for 3-dimensional, 4-dimensional it is in work of Patera-Winternitz, then 6-dimensional Magdarazanov. So, but what about 7, 8? What is maximum is done completely?
We don't have maximum is done. And if I may say something about optimal system, we are not solving. Some of these geodesics are simple. We're not using symmetries to solve them at all. As I said...
No, this is not symmetry. I want a classification of subalgebras. Optimal system of subalgebras. What is maximum dimension is done.
Maximum dimension, the one that I'm aware of, is the 7-dimensional nilpotent. Like, for example, we don't have a classification.
But it's particular case. It is particular case. I mean, for any.
We don't have, like, if you tell me, is there a classification for all 7-dimensional Lie algebras? No.
Yep. So 7 is not done, right?
So the maximum is done 6. After that, special cases.
Okay.
Thank you so much, Professor. I think
Thank
Matt
you
is
so
there.
much.
Always nice with Matt.
Just one comment, Dr. Kara, I believe we met one time in Saudi at KFU PM.
Your name sounds familiar.
All right. Have a wonderful day, everybody. Enjoy the conference.
You can speak.
Thank you so much. So next I'd like to introduce Dr. Matthew, it's Ali, Dr. Matthew Ibinu. So he's a postdoc fellow in the Department of Maths and Stats at the University of Regina in Canada. So his research has to date got a lot of awards. And I have to mention that he got his PhD in KZN because that's my home province. So nice to meet you, Matthew. Good luck. And he will be telling us about economic growth, the framework for economic growth with memory effects.
You say it together.
Yeah, no. Yes, look at it. It's not a KZN much. Thank you, Doctor.
Thank you, everyone, and appreciation to the organizer for the invitation. My name is Matthew Ibinu, and I'm presently at the University of Regina in Canada. I'll be talking today on the topic titled A Solution Framework for Economic Growth with Memory Effects. This will be the outline of the presentation. There will be a brief introduction, which is the motivation for the studying of solution model. And then the brief talk about the literature issue, that is, what are the works that some people have done on this model, and what are the necessary things that one needs to understand to understand this presentation, that is the current work, the current study on the model. That will be presented in this under the preliminaries. And then I move to the main results. To start with, the solution model itself is regarded as a cornerstone of modern economic growth theory. And this model, basically, it describes the evolution of capital per worker over time. It is an economic model, and it describes the evolution per worker over time. And the model serves as a foundational tool in both theoretical and applied economics. This model has been studied in various forms. Its classical form, that is, its basic form given by the ordinary differential equation, is this, where in this equation, K of t is the capital labor ratio at time t, where the capital KT, that is the K of t, is the capital labor ratio at time t, where the uppercase K of t represent the capital and L represent the labor. The other parameters in the model are positive constants, and they are wave functions, that is the role they play, will be discussed as we proceed. So they characterize the production function and the capital depreciation. Those are the roles that the P, Q, and M play in the model. Over the years, this model has been extended to a wide array of domains. That is, it has been applied. It's a model, although it's an economic model, but it has a lot of application. It has been applied to study a lot of problems, which include the climate change, the corruption, that is the modeling of the corruption, and also in education. Its role has been applied in economic growth and in resources exploitation. These are some of the domains in which the model has been applied. And these applications, they demonstrate the flexibility and the relevance of the model in capturing the long-term economic dynamics across diverse texts. These several studies have contributed to the enhancement of the analytical and empirical foundation of this. There are several studies that have been carried out on this. One of them is this study which applied the least square method to estimate the model's parameter. And in order to estimate the model parameter, they made use of the Penn word table, which the 2021 Penn word table. The Penn word table is a well-established source of economic growth data, which is being collected annually, and that has been since 1950. It has been collected annually, and they made use of that data in order to estimate the parameters of the solo-swarm model. And another study carried out on the model is which leverage on the ordinary differential equation, which is recently proposed the machine learning. It's also that one proposed a hybrid solo-swarm model. That was the main contribution. They proposed a hybrid one. And reports were also given on the analysis and stability of the equilibrium points of the model. That has also been studied, and the study has been carried out on that way as well. That is the equilibrium of the model. Their stability have been studied. And in order to still extend the model, the parameter Q, instead of being a constant, it was made to be a variable. So that is a time-varying labor good Q of T was introduced into the model. It's just as a form of generalization of the model, that in order to still generalize, in order to still improve its application. Despite wide application of the model, one of the challenges is that it formally relies on the classical derivatives. That is, most of the existing model, most of the applications in which the existing model which have been applied in various fields is rely on the classical derivatives. That is given by ordinary differential equation. And looking at it, complex dynamics in the real world, in economics, they are not adequately being captured by the ordinary differential equations due to the nature of the economy. That is, due to the complex systems involved in the real world economic system. They are not the ordinary differential equation does not really capture it well. Therefore, system exhibiting memory or hereditary behavior remain largely underexplored, because ordinary differential equation is limited to some extent in its application. It does not have the capacity to capture the hereditary property of a real world system or the memory involved in some real world system. Therefore, that makes the ordinary differential equation or the models given by the ordinary differential equation to be limited in their capacity. Fractional differential equation, in its own case, it generalizes the ordinary differential equation. It's a non-integer derivatives, and it generalizes the ordinary differential equation. They are powerful. That is, the fractional differential equations are powerful for modeling memory effects. And in economics, memory effects are particularly relevant due to looking at the real world economies. The memory effects they have the memory effects as their natural components. So many economics processes, such as investment decisions, consumption patterns, and even technological adoption, they exhibit long-term dependency. That makes it certain that that ordinary differential equation does not really capture all the memory effects involved in these systems. The motivation now is that, can we propose studies that incorporate memory effects into the solo-swarm model using fractional derivatives? That was one of the motivation. Is it possible that this, since the many of the reward systems, they involve memory or hereditary properties, is it possible to involve memory into the solution model, using the fractional derivatives? And is it possible, can the model behavior under the integer and fractional or fractional order form be compared? Once we come up with this model, is it possible to be able to compare how they relate, what is the improvement that the fractional model we have on the models given by the ordinary differential equations? And also, can we come up with the study that offers new insights into capital accumulation when historical influences matter? So these are some of the motivation that propelled us into this study on economic growth using the solution model. In order to understand for better understanding of the main result, we need the following idea about the field. Given f as a set of functions with the suitable growth, the smooth transform of a function k of k in f is defined by this equation 3.1. This is definition of the smooth transform. Given a function k, a smooth transform is given by this 3.1. This smooth transform, as it is, obviously it is an integral transform. And for a given function k, since it is an integral transform, let's relate it to one of the well-known integral transform, which is known as, what connection does it have with a well-known integral transform, which is Laplace transform? If we denote the smooth transform of a function k of t by this upper k of u, and the Laplace transform of k of t, if we denote it by L of u, then the dual relation between the smooth transform and the Laplace transform is given by this and this. These are the relation between the smooth transform and the Laplace transform. The smooth transform, one of its essential properties which makes it appealing and which motivated its use in this study is that it preserves units of the original function. And looking at the Laplace transform, one of the challenges is that it changes units, but smooth transform in its own, it preserves unit, and preservation of unit is very essential. That's that we apply the smooth transform in this study. So unit preserving property of smooth transform is very useful in economics and many physical applications where the dimension consistency is very important. So the smooth transform has a more straightforward inversion process, even compared with the Laplace. So these are some of the motivation for the use of the smooth transform rather than the well-known Laplace transform. Throughout this presentation, we shall refer to R as the set of real number and N as the set of the integers. For the smooth transform, which some might not be familiar with, let's just look at the smooth transform of some selected functions. Given a function k of t, and what are the smooth transform? For example, 1, the smooth transform of 1 is 1, and given a function t, its smooth transform is u. And given this, that is t to the power n divided by the gamma function of n plus 1, which is n factorial, its smooth transform is simply u to the power n. And the exponential at, its smooth transform is given by this. For the sine function, its smooth transform is also given by this. And for the cosine function, at is given by this. And for this exponential function also, where b is different from a, its smooth transform is given at this. So with that, we can see that smooth transform is much like the Laplace transform, but it has some advantages over the Laplace transform, like unit preserving property, as well as its inversion, which is easier compared with the Laplace transform. For the nth order derivative, its smooth transform is given as this. For nth order derivative k, the smooth transform is given by 3.2. And look from this definition, that is from 3.2, if for the first order, that is simplifying, for the first order case, that shows that the smooth transform will simply be this 3.3. That is 1 over u into ku minus k of 0. And for a function kt and alpha is 0, the capital derivative, which is the fractional derivative that is used in this study, the capital fractional derivative is defined as this. This fractional derivative, its smooth transform is given as this. And for the convolution, let's talk about the convolution, the convolution products. Given psi and mu, and the convolution product is defined as this. And the smooth transform of the convolution is also given by this equation. We also need the important definition, the Mittag-Leffler function is defined as this. And we have the following properties, these well-known properties about the Mittag-Leffler functions and their smooth transform. In this one, the proof are repeated here, but because they are well known. So the smooth transform of this is given as this, and this one is also given as this. So we are going to make use of them as well. And lastly, we want to talk about the Adominian decomposition. If we have this term n of k to be present in a differential equation with a solution series, with a solution expressed as the power series like this, the coefficient an in this place are known as the Adomiad polynomials. And these polynomials, they handle the nonlinear term, which is defined an, that is, this an is defined as this, which is the Adomiad polynomial, is given that its definition is given as this. The first few terms of this polynomial are a0 is simply f of k0, and a1 is given as this, a2 is given as this, a3, and so forth. So each polynomial, looking at them, each polynomial depends on k0 to kn, and that enables the recursive construction of the series solution to nonlinear problems. For the investigation of the classical models, so what are the main contribution of this study, of our study on the solution model? The first thing is we investigated the classical solution model. That is, the model is classical form. That is the model given by the ordinary differential equation. We study its property. And the next thing is we extended this model to fractional calculus. Extension of the model using fractional calculus in order to incorporate the memory effects. And also, we consider the derivation of the analytical solutions for both the classical and the fractional models. And development of we develop a hybrid method, because solution model in itself is a nonlinear model which defines some well-known analytical solution. Therefore, we develop a hybrid solution. We apply the method of differentiation of smooth transform and Adominian decomposition method. We apply the differentiation of them, that is the completion of them, in order to obtain the solution. So we give the analysis and the impact of the fractional derivative on the dynamics of the capital accumulation. The classical solution model capital accumulation model is given as this. And this model, looking at it, if we equate it to zero, that shows that it has two that is, the equilibrium points are given as this. And this is the graph for the equilibrium points of the solution model. Due to the non-linearity, as I've mentioned before, this model is non-linear in nature, and that makes it to resist some well-known standard analytical techniques. For the model, the approximate solution, that is, we apply the method of the hybrid of the Smoot transform with the Adomia decomposition method. So for this model, that is for the classical model, of the solution, we obtain this solution. That is the approximate analytical solution for it is obtained as this. And for in order to study for the numerical experiments, for the numerical simulation of the model, we assign for the assignment of the parameter in the MATLAB. MATLAB was used for the assignment of the parameters in the MATLAB. We obtain the data from the following sources. One, statistical data from the OECD economic outlook. That is Economic Cooperation and Development. Organization for Economic Cooperation and Development. We obtain the data from there, statistical data from there. And also, we also obtain the parameters. We use the parameter value that have been used in studying the solution model with the Cobb-Douglas type production functions. So those are the ways, where we use the data. And for the model, we have this. That is for the solution for the classical model, we have these graphs. That is, the first one is the graph of K of T. That is where Q, we plotted this one against T and Q, where P and mu, they are hedge fixed. And for the second one is the graph of KT of P, where Q and mu are fixed. So what are the insights from those two graphs? We observe that the surface plots highlighting the contrasting roles of the production. P is for the production, and the Q, depreciation Q, in shaping the capital dynamics. The first one is for K of TQ, and while the second one is for the K of TP. They have the contrasting effect, the role. What are those things what are the contrasting effects that we observe? Now, the plot of K of TP, it shows that where the Q and mu are constant, it shows that higher productivity accelerates the capital accumulation. That reflects the positive impact of the technological progression and investment efficiency. And the graph of K of TQ, where the P and mu are held constant, that shows that we observe that the higher depreciation rate, Q, is slow or it reduces the capital growth. That underscores the effect of the capital obsolescence and the need for reinvestment. The classical model assume that the reason now why the reason that for the motivation, that is, we propose the fractional model. Why we propose the fractional model is because the classical model assume that the capital evolves solely based on the current state of the system, and that neglects the influence of the past. So, many reward economic processes, they exhibit memory or inertia or even the path dependency that the classical model cannot effectively capture. In order to incorporate this all this one, or that is all the memory effects in the real world system into the model. We reformulate the classical model using the fractional derivative. Specifically, we made use of capital fractional derivative. And the capital fractional derivative is the choice because it naturally handles the initial conditions in the same form as ordinary differential equation. And that facilitates both the theoretical and numerical analysis. And therefore, we came up with this model. That is, this is the fractional form of the solution model that we proposed. D of alpha, it denotes the capital derivative of order alpha, where alpha is in 0, 1, 1 is included. And when alpha is equal to 1, this model, it reduces to the classical classical solution model. That's justified, that's validated that this is a true extension or a generalization of the true or of the previous model of the classical model. And we can see that when alpha is equal to 1, the classical model is being recovered from it. That shows that this extension is a true generalization of the classical model, since we can recover the classical model from it by taking a special case of it. Therefore, for alpha is in cell 1, the solution of the fractional model is given by this. We obtain the solution as this. So we have already previously obtained the solution for the classical model, and for the fractional model, the solution for alpha in cell 1, the solution is obtained as this. And we also did the simulation of this model as well. For the graph of K of TQ, where in this case, P, alpha, and mu are head constants. The figure shows that this graph is shows the dynamic part of the capital accumulation over time t, and we have had the depreciation. Take note that Q represents the depreciation and P represents the productivity, and mu, it represents the capital elasticity. And in this model, alpha is just the fractional order. So in this one, we have that this is the graph of K of T, TQ, where P, that is the productivity, the fractional order, and the elasticity are head constants. What are the insights from that? One, lower values of Q leads to faster growth in capital per worker, as capital erodes more slowly. And also, higher Q slows growth of the KT, which emphasizes the dampening effect of the stronger depreciation. And the fractional order alpha, the effect it has on this model compared with the classical model is that fractional order, that fractional alpha, it adds memory to the system, which produces smoother and more gradual capital dynamics than the classical model. So overall, the visualization highlights how sensitive long-run capital accumulation is to depreciation and how fractional calculus captures the memory dependence in economic systems. Also, we consider that is the simulation for the K of TP, that is why the Q, alpha, and mu are head constants. This graph shows that is the graph of this, that is capital, how capital evolves over time, and we had the Q, alpha, and mu constant. The insight from this is that one, higher P, that is productivity, strongly boosts capital accumulation by raising the return to existing capital. And lower P slows or stores the capital growth, as output cannot fully offset depreciation. And the effect of the fractional order on this model is that the fractional order derivative introduces memory that allows the past investment to shape the current dynamics. So this behavior departs from the classical solution model by capturing the persistence and smoother transition. which better reflect the real world capital evolution. And we also consider specifically the effect of alpha, that is the fractional order on the model. In this case, the effect of the fractional order is being considered, while PQ, that is productivity, depreciation, and elasticity are held constant.
Dr. Matthew, sorry to bother you, but your time, you've got a few more minutes.
Okay, thank you. So the effect of the fractional order is that increasing alpha shifts the system from memory effects towards the classical solution behavior. That is, as alpha increases from 0 to 1, the models increases, that is, it moves. It shifts towards the classical behavior, that is the classical model. And for small alpha, capital goes more slowly due to stronger historical inertia. And as alpha approaches 1, the model responds quickly, resembling the memoryless classical case. So this fractional framework captures memory and path dependence, which provide a more realistic view of the long-term capital dynamics. And lastly, we consider the effect of the elasticity. For the elasticity, we observe that as mu increases, the curve steepens, indicating the stronger output responsiveness to capital in the production function. And at low mu, capital, that is at low elasticity, capital accumulation remains modest and consistent with diminishing return, while the higher elasticity yields rapid capital growth, reflecting stronger return to scale. So, in summary, many economics models exhibit path dependence and delay responses, and these are not fully captured in the classical solution model. So we extended the model by introducing the memory through the use of the fractional order derivatives. And using analytical expansion and 3D numerical simulation, we show how parameter changes influence capital accumulation path. And the fractional models, we saw that it preserved the long-run growth characteristics while capturing the inertia and persistence seen in real economics. And this framework, it opens new direction for empirical calibration and theoretical development, especially in the context where historical dependence and gradual adjustments are essential. So this presentation is a published result in 2020. It was published in 2025, and in the African Mathematica, and the co-authors, that is the collaborator for this study, are Kevin Duffy, who is a professor of mathematics at the University of KwaZulu-Natal in South Africa, and Sibusiso Moyo, also a professor of mathematics at Stellenbosch University in South Africa as well. Thanks for listening.
Thank you so much, Dr. Matthew. Do we have any questions online? No
If
hands?
no
Any
questions, may I ask? One question is the following. One of the problems related with fractional derivatives and fractional equations is to prove theorem of existence. What about your case? Does it exist solution? Because in slide number 34, you wrote series. Is it convergent, this series?
Yes, in the literature review part, where during the presentation, I talk about the previous work that has been done on the proof of the existence and uniqueness of the solution for the fractional model. And the model that we use, we made use of the fractional model derivative, which which has some characteristics that are similar to that of the classical model. And for the capital fractional derivative, it's a model, it's a derivative that have been studied a lot, whose existence and uniqueness have been studied. So, and we made reference to it in the course of the literature review. And the more details about it is in the full paper.
So am I right that your answer is there is no such kind of definition? Okay, thank you very much.
Okay, thank you, sir.
Thank you. Any questions? Yeah. Okay, you got a question?
Thank you, Professor. Nice presentation. My question is about that in your motivation, one of your motivation to study this research is that about the fractional modeling that preserves some memory of facts. Okay.
Yes.
But the delayed differential equations also modeling such type of which have also some memory of facts. So why the model is not problem is not model with delay ordered differential equation using classical derivative, and why you need to fail to model your problem using fractional derivatives?
The motivation for the study, what I stated as the motivation for the study is that looking at the classical solution model, it does not capture some of the, it does not fully capture some real-world system because of its, in its classical form, it does not capture some of the real-world system, because many real-world system, they involve memory, that is, they involve inertia. That is, looking at the real-world system, some, for example, the economics, the present state of the economy it's not something that is just happening it's not something that is just happening today. It's based on what has been happening before. For example, if a government just take over the government, yes, the way the person is going to run the economy, it will have the effect of the previous economy will have effects on some of the economy of the present system. So that is looking at the classical model, it does not fully capture that. In order to propose a model that is going to capture that, that's what motivated the study of fractional model. That is by using the fractional order to introduce the memory into the model.
One more question, may I ask? Can
Is it related?
yeah.
Is it a different question?
Okay. Okay. Prof, you use a domain polynomials in a series form. Okay. But it means you are working in some type of vector space. Okay. But the vector space does not give us the generic rule to add infinitely many vectors. Okay. It only provides us a rule to add finitely many vectors. So you use infinite series, you are adding infinite vectors. Okay. So my question is that what criteria you impose to take the finite sum? So which criteria you to consider the infinite sum? Because there should be some criteria.
For the simulation, we just take we take the first few, yes, we take the first, I think like the first 5 elements is what we use, because from the computation, we observe that taking more elements does not add more contribution to it. That's also we took the limited number that really counts for the simulation, like the first 5 terms were used for the simulation.
Thank you, Dr. Matthew. I think if anybody else has questions, maybe you can contact him. I can see some hungry people on this side. Thank you, Dr. Matthew.
You're welcome.
And thank you to all our speakers online and in person. We're going to have lunch now. To those online, we'll return at 1:30. Thank you very much. Just to those guys that are here, just 3 quick announcements. One, they let me know that, so they've allocated tables to us. So it's only the 5 tables as you go out here in a row. Don't go sit at the other tables for other people. That's one. Number 2, if you haven't noticed, we organized some cables and things. There's obviously not enough for everyone, so sharing is caring. That's what Barney says. So just move around, and if you need to charge your laptop, do that. Then I forgot what the third one was. No, thanks everyone.
Our speaker now from University of Cape Town is Jean-Jacques Duplessis, whose topic is, I think as displayed there, energy spreading in nonlinear disordered Klein-Gordon chains with long-range interaction. Jean-Jacques is a PhD student in the, you have a group, the nonlinear dynamics group at UCT.
Yes.
Wonderful. His doctoral research is on the dynamics of one-dimensional Hamiltonian lattices with emphasis on the effect of long-range interactions. You're going to explain that to us.
Great. Oh, thank you. My name is Jean-Jacques Duplessis. I'm a PhD student in the Nonlinear Dynamics and Chaos group at UCT. Today I'll present to you some of the work that I've done on energy spreading in nonlinear disordered Klein-Gordon chains with long-range interactions. And this work was done in collaboration with Eleni Christodoulidis, Tasos Buntes, and Haris Kokos, my PhD supervisor. So a quick outline of my talk. I'll start by going through some of the background on the Klein-Gordon, the disordered Klein-Gordon DKG system with nearest neighbor interactions, which has been thoroughly studied. I'll summarize some results on the normal modes of the linear version of the system, as well as how energy spreads in the nonlinear system. And then I will introduce the DKG system with long-range interactions, and then present some of the same things, such as the normal modes and the energy spreading, to see how those results differ when we add long-range interactions. So let's start with the nonlinear disordered Klein-Gordon chain, which is just a 1D lattice with nearest neighbor interactions. The Hamiltonian is given over here. It is a conservative Hamiltonian system. And this diagram at the bottom is just to help us visualize that this is essentially just a bunch of coupled oscillators. The interactions here are represented by these springs. So you see here in the Hamiltonian that we have each site, there are n sites in this chain. We have some kinetic energy, some on-site potential energy, and some coupling potential between pairs of nearest neighbors.
Can I give a root?
Yep.
You should say no. So how would that be an equivalent of a discrete Hamiltonian? I see like jump.
It is a discrete system in the terms of like we have a discrete number of particles, a finite number of particles. So we were talking about ordinary differential equations, not partial differential equations. That's.
But it's got those jumps, right? Which is basically lattice.
Yes, yeah. So we have a lattice here, and these Qs tell you the displacement of each oscillator from equilibrium, basically. And what's interesting about this is that we have these epsilon parameters. These parameters are drawn uniformly at random from an interval 1 minus d to 1 plus d, where d is some small number. And that causes the on-site potentials to be slightly different from site to site. So it models disorder in the lattice. And this has been applied to some physical systems like certain molecular crystals and whatnot. The parameter W controls the coupling strength, and we have fixed boundary conditions. Something I'll just also note is that whenever we choose these epsilon values, at random, of course, this is known as a disorder realization. Each time we choose a different disorder realization, we have a slightly different lattice. The equations of motion for the system are given here. J is an index which runs from 1 to n. And these are nonlinear equations because we have a cubic term over here. But if we want to study the underlying linear system, we could just drop the nonlinear term, and we get the following equations, which of course you could write as a vector equation. And this here we have a matrix A. The eigenvectors of this matrix are the normal modes of the linear system. Those are just fundamental solutions where each mode represents a collective oscillation of the system with a characteristic frequency. So something interesting about disordered systems and the normal modes is that the normal modes are localized when you have sufficient disorder in the system. So here on the right, I have a nice figure from this paper, which shows some profiles of normal modes for different values of D, where D controls the disorder strength, essentially. So here's a very disordered system, and here's something that's it's close to an ordered system. D equals 0 would correspond to an ordered system. The more disorder you have, the more localized your normal modes are. And that actually has a direct effect on energy spreading in linear lattices. It's a phenomenon known as Anderson localization, where localized excitations of a linear disordered lattice remain localized. When you add non-linearity to the system, though, then those normal modes, which were previously uncoupled, do have some coupling then, and then Anderson localization is broken, and you will see energy spreading in the non-linear system, which I will talk about now. Just a quick note about energy spreading in the nonlinear system. The way that energy spreads, the characteristics that you see, actually depends on the initial conditions that you use and the parameters that you use. But more or less, these behaviors can be categorized into three distinct dynamical regimes known as self-trapping, strong chaos, and weak chaos. I'm not going to go into too much detail here, other than to say that while I am interested in all of these regimes, I will just present results for the weak chaos regime today in the interest of time. So in order to understand how the energy is spreading, we define the following quantity psi k, which is the normalized energy distribution. It's just the fraction of the total energy which we associate with site k. And here is the definition over here. Each site has its kinetic energy, on-site potential energy, and then we halve the couplings with its nearest neighbors. Here is a figure which shows the time evolution, just an example of the time evolution of the energy distribution. So here we have time in log scale. Horizontal axis represents lattice sites, and then the dark color means lots of energy. The light color means little energy. And we can see here that we start with initially a localized excitation in the lattice, where we excite a few sites in the middle. And then over time, we can see that the energy spreads from the middle outwards, and the energy distribution gets wider. And at the bottom here, we have 3 snapshots in time of the energy distribution. These colors correspond to the dashed lines in the top plot. So you can see how the energy distribution gets wider over time. One useful way to quantify how this energy distribution is growing is we can look at the quantity called the second moment, which is basically just the variance of the distribution that can tell us how the distribution is spreading. And we also define the participation number. The definition is here. Basically, this is a measure of how many sites strongly participate in the distribution. So if you excite one site, participation number is 1. If you excite 13 sites and give them the same amount of energy, participation number is 13. And here are some results for this nearest neighbor system in the weak chaos regime. A number of different cases for the second moment here and the participation number. And we can see how these numbers increase over time. And it turns out they increase according to power laws. So t to the 1/3 for the second moment and t to the 1/6 for the participation number. And we're curious what happens now when we go to long-range interactions. So we've gone through all the background. Let's talk about the nonlinear DKG system with long-range interactions, which is defined by the following Hamiltonian. Looks very similar to the one before, except now we have coupling potentials between every single pair of lattice sites. Although the strength of that coupling is attenuated by the distance between the lattice sites. So in other words, sites K and sites L are coupled, but that coupling is scaled by 1 over the distance between them to the power alpha. Alpha here is a parameter which determines the range of the interaction. So large alpha means very short range interactions. Small alpha means very long range interactions. And this system has been studied before, but as far as I know, only with ordered systems. So we're also adding disorder to this now to see what happens. So just to give you a quick visualization of what the couplings look like, we can of course add nearest neighbor couplings, and then next nearest neighbor couplings, which are a little bit weaker, and next nearest neighbors, et cetera, until you end up with a mess and all sites are coupled with all other sites. Just note that the nearest neighbor system is a special case of this general long-range interaction system. If you take the limit as alpha tends to infinity, all of these terms vanish except for the ones where the distance is 1. So you just recover the nearest neighbor interactions in the limit as alpha tends to infinity. So let's start with the normal mode results for the long-range system. On the left here, I have the normal mode frequencies for each of the normal modes. Here I'm using a lattice of size 1024, and I've indexed the normal modes in increasing order of their frequency, and the different colors represent different interaction ranges. So alpha infinity is the nearest neighbor interactions, and then as we go from green to blue to purple, pink, and red, we are increasing the range of that interaction. And then on the right, I have a few normal mode profiles. And we can see from this green profile here, and this blue profile, and this purple profile, that they are very localized. One way to quantify that is to think in terms of the participation number in normal mode. I defined those originally in terms of the energy distribution, but if you just use the normal mode profile as a distribution, then you can apply those indicators to quantify, to measure the kind of locality of these distributions. So for the green, the blue, and the purple, the participation number is small. Very few sites are involved in that distribution, but also the second moment is very small because it's not spread out very far. But when we get to these longer range interactions like pink and red, so let's look at red, for example, we see two peaks that are far, far apart. That means participation number is practically 2, it's very small. Second moment is large because these are spread out. And going further, we can calculate participation number and second moment for all of the normal modes. These are actually even averaged over 20 disorder realizations each. And for the participation number, as we go from the green down to the red, so as we're increasing the interaction range, we do see overall for most normal modes, the participation number seems to decrease a little bit, not significantly, but there is a very noticeable difference with the second moment. So when you go from green, its nearest neighbors, all the way up to very long range interactions, the participation number increases significantly. So finally, I want to talk about the energy spreading in the nonlinear LRI system. Here I have some color plots like before, where I have the time evolution of the energy profiles. On the left, I have the alpha infinity case, so nearest neighbor interactions. And then as I move to the right, I'm increasing the range of the interactions. And then at the bottom, I have some snapshots in time corresponding to the dotted lines for each of the color plots. Notice that these first two panels look very similar. We see how energy, and initially we excite a few sites in the middle, and then energy slowly spreads outwards, basically from site to site to site over time. Whereas for the longer range interactions, we see some interesting behavior. One being just that a little bit of energy seems to immediately get imparted to the rest of the lattice as a whole. But then later on, we also see these vertical spikes appear, these dark spikes, indicating that these sites get highly excited. But because we have all of these gaps between them, they're getting excited without necessarily exciting all of the sites in between the initial excitation and that site. And we see that for this case as well, all of these vertical stripes. We can also compute the second moment for these distributions. And here I have some results, which are the average of 20 disorder realizations. So this is nearest neighbor interactions all the way up to long range interactions. And this is the average, the black line, and then one standard deviation away is the shaded region. And at the bottom, we have the derivative of these figures to just understand what is the slope of the straight part of this line. And we can see here by the dotted line that it is a slope of approximately 1/3, which is what we expect for the nearest neighbor system. And so we see this behavior persists for a while as we increase the interaction range. But eventually, when we go too far with our interaction ranges, then the system tends to behave quite very differently. We see the second moment increasing much faster in these last two panels. And we see very similar results for the participation number, where for shorter range interactions, we get the same results that we would see for nearest neighbor interactions. And then for long range interactions, the behavior tends to end up quite differently. So in conclusion, the energy spreading characteristics that we looked at, particularly using the participation number and the second moment for the nonlinear LRI system with short ranges, are very similar to that of the system with nearest neighbor interactions. The normal modes in the linear LRI system are not localized for very long range interactions. And that actually had an effect on the energy spreading, where we could see how energy could get transported very far in the lattice without exciting all of the sites in between. And so, yeah, as a consequence, we saw that nonlinear LRI systems can spread between spatially separated sites without passing through all the sites in between. Here are some results, particularly for the nearest neighbor interactions and the work that has been done on this topic, and also here on the long-range system. And just to acknowledge my funding sources and the computational resources used for this project. But thank you for your attention.
Any questions from the audience?
Can I ask, in terms of the distribution of the energy?
Yep.
And have you observed bimodal or multimodal distributions instead of
in the energy profiles that you see? So with the types of excitations that we're doing, we're starting with an initially localized excitation. So are you saying that does it spread and maybe have these two separate things? I haven't looked for that specifically, because what tends to happen is that the energy will spread from the middle and start thermalizing the lattice over time. I haven't observed that in particular. What I will say is that for the long range system, you do often see these this kind of behavior where the lattice doesn't necessarily thermalize, where you have lots of peaks, basically, where it's excited here and then not excited, then excited, then not excited. But I haven't explicitly observed a bimodal distribution.
So a follow-up question is, I suppose that's a parallel interaction parallel range, yeah?
The way, yes, that's the one over the distance to the power alpha. Yes, yes.
That's because your physical system.
Yes, this, I believe it's been applied to model things like dipole interactions, when the specifically the long range system. So they have applications there, yeah.
Because in biophysics, people sometimes use exponential.
Right.
Exponential. Does that change your system behavior?
I haven't looked at an exponentially attenuating interaction, no. But that might be an interesting.
Very interesting.
Thank you.
Okay, one more from here, and then the online. Are you Frank? Do you ask questions?
Oh, may I ask questions?
Let's just get one local question, and then we'll get to you, Sergey.
Sure. Yeah, so I want to ask, do you vary the distribution of these of epsilon, right? So you do it on the interval 1 minus d, 1 plus d.
The epsilons.
Yeah, so when you make the disordered lattice.
Let's go back there. Yeah. So what about this? This is a uniform distribution. We're sampling from a uniform distribution.
Have you tried other distributions?
No.
The reason I ask is because in some of these disordered systems, the way in which you choose these can affect the way in which some wave travels through, and has to do with the autocorrelation between subsequent disordered points.
Right. So would that be in a like a statistical set? Because what we're doing a lot of the time is we calculate this for many disorder realizations and average the results, so we can get kind of general behavior for how the energy is spreading, for example. So maybe that, I don't know if that would have a kind of statistical effect on the results that you get after you average many cases.
Yeah, this is something we can talk about afterwards. Yeah.
The good thing about this place is these two guys are from Cape Town. They meet up here.
Come knock on my door next time.
This is a wonderful place to be. It's a good forum. I think just have a chat afterwards and then go back together and take it down.
And was it, yeah, is it Sergey that has a question? Question online?
Oh, yeah. May I ask a question? Actually, I want to know
Yes.
how did you calculate these solutions like QK and PK? How did you use a random variable of epsilon? You have random coefficients. It means that maybe you are doing numerically. On each step, you have
Numerically. We're doing it numerically.
In each step, you use a random representation of epsilon, right?
No, that's a good question. No. So the lattice is set up with these epsilon values at the beginning, and then they remain constant the entire time for the numerical integration.
Oh,
so
okay.
this defines the lattice. The disorder realization defines the lattice at the beginning.
Okay, thank you.
Thank you.
Very nice talk. Thank you very much. The next speaker in this session is our real chief organizer of the whole business. Ali was going to speak about reduction via the one-dimensional optimal system of subalgebra. And this is too long a time, not it?
Yeah.
Etc.
Yes.
There. So this is another one of our symmetry directed talks, as opposed to.
Okay, can go.
Just imagine.
I need to now share the slides. Stay done. Yeah, no, it's that. Yeah.
It's to you.
Yeah, thank you.
That's why you wear the top.
Yes. I'm sorry. Sorry, no worries. Thank you so much. Thank you, Professor Kara, for such a nice introduction. So the title of my talk is Reduction via One-Dimensional Optimal System of Subalgebra of the main algebra for the physically interesting partial differential equation. This is the outline of my today presentation. The first thing I will talk about the classification of Lie symmetry algebra, and then I will talk about the optimal system of subalgebra, and then I will talk about the reductions under optimal system, and I will also mention why we require to construct optimal system for reducing the partial differential equations under the optimal system of subalgebra. Okay, so in the 19th century, the Norwegian mathematicians obviously studied the continuous group of transformation that leaves the differential equations invariant, which is known as Lie symmetry analysis. After that, the Russian mathematicians, Osyankov, developed the methods in a very systematic way. So there was a big gap between Firstly and Osyankov developed the method in a very systematic way, and he introduced the idea of optimal system of subalgebra. He was the first guy. Osyankov was PhD advisor of Neil Ibragimov, and from 1994 to 2000, he was in South Africa at University of Witwatersrand, and Peter Leach worked at Wits University from 1990 to 2003. And Neil Ibragimov and Peter Leach are the teachers of Professor Fazil Muhammad and Abdul Hamid Kara. So Professor Fazil is my PhD advisor. Professor Kara is my co-advisor. So I learned these things from Professor Fazil, Professor Kara, and I'm still learning many things from them. So the first thing I want to mention, the richness of the method. So the Lie symmetry method, the first thing is it helps us solving a partial differential equations, non-linear partial differential equations, and ordered differential equations, particularly higher order order differential equations and partial differential equations. So we can find the solutions, and those solutions has very important property which are called the invariant solutions. And we can also find the optimal system, and the what is the benefit of finding the optimal system? It provides us the general class of the solution, which is actually the bigger class of the solution. And then the next thing is solving fractional differential equations. So we can also solve fractional differential equations. Gazizov and many other people, Professor Kara and many of our other colleagues in this group working in fractional differential equation, and they are solving using the least symmetry analysis and finding the solutions for the fractional differential equations. And third thing is finding continuous symmetry and the general solutions of the difference equations that Professor Kara presented in this morning. Then we can do the double reduction using conservation law. We have two first major approach, which is the most elegant, is the variational approach. We find the Noether symmetries, and then we reduce the reduce doubly, which is called the double reduction, and using the variational, by finding the variational symmetry. And then the second approach is multiply approach. Many partial differential equations does not have Lagrangian, because the first problem associated with the Lagrangian. But if we don't have Lagrangian associated with the partial differential equations, we use the multiplier approach to reduce partial differential equation doubly. Doubly means for the single reduction, we are reducing the partial differential equations by independent variable. So in double reduction, the equation reduced by two independent variables. And then we can also solve dynamical system using partial Hamiltonian approach. Many people are working in this direction as well. And then we can construct exact solutions of the equations in general relativity. So Andronikos, who will be presenting tomorrow, Professor Andronikos, who will be presenting tomorrow, is working in general relativity. Okay, so this is my problem. So one-dimensional space, the nonlinear wave equation can be written in this way, where this is a phi of u, which is a which build actually the non-linearity, and it's a arbitrary functions. And in the one-dimensional space, this equation reduced to the following form, which is called the one-dimensional non-linear wave equation. So for the linear wave equation, we have several methods: separation of variable, Laplace transformation, integral transformations. But these methods are for solving linear wave equation, but they have some limitation. These methods are limited, less effective, or even fail sometimes when applied to the non-linear partial differential equations or non-linear wave equations. So these methods are for non-linear partial differential equations, but our focus is on linear least symmetry analysis. So using least symmetry analysis, which is actually more algorithmic and general technique to solve non-linear partial differential equations, and it provides us the exact analytical solutions. Okay, so first we studied this problem, and we presented this symmetry classification optimal system of subalgebra of the main Lie algebra, which we classified by classifying the arbitrary phi of u I mentioned in the main problem, in the main model. And then we presented the form of invariant solutions, and then we also presented the conservation law using the multiplier approach, because the variation is not attached with the wave equation, because this equation does not have Lagrangian associated with it. So this work is done and published in a very good journal. And then we extended the problem to fourth order partial differential equation by adding the higher order fourth order dissipation terms. And we also performed the same analysis. So we struggled to submit this work. So we are trying for 1.5 years. So first it was a many big articles, so consist of 65, 70 pages. Then we were struggling to publish it. It was a big paper, but we reduced it to 2 articles. And now I just received the acceptance this morning. The first part of this problem is accepted, and the second part is still under review in one of the journal. Okay, so this is the algorithm. So we have a symmetry, and then we use the least symmetry criteria, which is already presented by Professor Shivu, Professor Kara, and Professor Riyad. And then we use the extended prolongation operator, and we use this equation to find the determining equation. Okay, so when we have this second order prolongation, because for the second order PD, we require a second order prolongation. And these are the extended infinitesimal. So when we apply on these, so we obtain the system of equations which are comparatively easier to solve, right? So when we solve these equations, it is easier to solve these equations instead of solving the main equation. So now we're using this method, we solving, and by solving these two equations, this system provides us this equation, which is a type of general equation. And now from this, we can construct many cases based on the values of phi of u, which is the classification problem actually. So first we solve the system determining equation for arbitrary phi of u, which provide us the principal algebra. So for arbitrary value of phi of u, we obtain three symmetry which construct the principal algebra for arbitrary value of phi of u. Then we have we build many cases here, and we constructed many values of phi of u. For this value of phi of u, when we have an exponential nonlinearity, the algebra extended to 4-dimensional. And then for second case, we obtain the function, which is the power law nonlinearity, and in this case, the algebra also extended to the 4-dimensional. And then we have two particular cases which we which arise in this classification problem when u raised to power -4/3, the algebra extended to 5th-dimensional. So this is very important to find one function which extend the algebra from principal to higher dimension. So then for another value of the phi of u, we have u raised to power -4, and algebra also extended to the 5th-dimensional. So this is the classification corresponding to phi of u in a partial differential equations. Okay, so now we have symmetry classification. But in this symmetry classification, we obtained third-dimensional principal algebra, and then extended to 4-dimensional, 5th-dimensional. So according to first fundamental theorem of Lie, we can find exact solution corresponding to each symmetry. But some of the Lie symmetry generators are equivalent, means this symmetry property and invariant solution property says the symmetry map one solution of the same differential equation to the another solution to the same differential equation. So if a symmetry is mapping one solution to another solution, it is we are saying these two solutions are equivalent. They are not different, but they are equivalent. So in order to construct inequivalent, or in order to find the set of inequivalent solution, we first classify the Lie symmetry generator into inequivalent classes. And once we construct the set of inequivalent classes, we find the optimal system. And once we have the optimal system in our hand, then we can find the inequivalent set of solutions, which represents the general class of solutions. And that's the most important set that represents the solution. So one thing which is important to mention here, in partial differential equations, nonlinear partial differential equation, we don't have principle of superposition. So by principle of superposition, we can't find all the solutions, right? So this problem is equivalent to finding all the solutions because the principle of superposition is not valid here. So in order to find, or in order to desire to find all the solutions of a partial differential equations, we construct the optimal system, which is actually the classes of the Lie symmetry, and then the solutions we obtain represents the general class of solutions. And that general class of solutions represents almost all the solutions of the solution. All the solutions of the partial differential equation. Okay, so we required the Lie algebra, Lie subalgebra representation theory, and a particular kind of representation we require in this is the adjoint representation, which is defined in this way. This is a representation which preserves the bilinear operator, which we define here actually. So you know, in algebra we have a bilinear product, but here we have this bracket, and this bracket commutator is actually a bilinear product here. So that preserves that product. So we define the adjoint representation, and we define the definition which actually represents the equivalent symmetry generators. If the adjoint action on the one symmetry is equivalent to the another symmetry, we say that these two symmetries are equivalent, right? So we define the definition of equivalent symmetry generator, and then we extend the definition to equivalent subalgebra. So in this way, we can define the optimal system of subalgebra. For example, family of subalgebra is an optimal system if any subalgebra is equivalent to some x of alpha for some alpha, and x alpha and x beta are inequivalent for distinct alpha and beta. And these two important properties, the first property represents the completeness, and second property represents the uniqueness. It means we obtain the complete set and we obtain the unique set, right? So this is how we construct the adjoint action operator, and then we use the adjoint action operator to find the adjoint action table using the so we can define the adjoint action using the adjoint action operator. First, we need to construct the adjoint table. So then we find the representation, and then we find the optimal system. Okay. So these adjoint action, we require the non-zero commutator commutators from the main algebra. So first we are trying to find the optimal system for the principal algebra, means for the arbitrary value of phi of u. Okay, so we constructed the adjoint action, and that I defined previously. So we start with the general element from L3. Why we are starting from the L3? Because the principal algebra, the main algebra, is from the three-dimensional Lie algebra, L3. So we take a general element, and then based on the coefficient A1, A2, A3, we construct all the possible cases to find the unique and the complete optimal set of subalgebra. Okay, so in the first case, we obtained 4 classes, and these set represents the complete represent the optimal system for the first case when the value of phi is arbitrary. And here is the here is a case diagram. We have here 4 cases. One when the A3 is not 0, and then in the process we find the value when we build the case A1 is not 0. So these constructions you get in the process of finding the optimal system using the adjoint table and the adjoint action. Okay, so first we start with this case and we apply the action, and we keep applying the action so that we can find all the we can construct all the equivalent classes of if this element is equivalent to this, it means it falls in the same class. So we will keep reducing the class unless we can get the element which is not further reducible. So it means if we obtain the element which is not further reducible, it means this is the first candidate for the optimal set of subalgebra. So in the similar way, we will construct all the cases, and so that we can find the optimal system of subalgebra. So that was the first case. And then in the second case, for when the value of phi is exponential nonlinearity, and we have 4-dimensional algebra, and these are the 3 non-zero commutators. And similar way, we will construct the adjoint table, and then using the adjoint action, we take the general element from the L4 because the main algebra is 4-dimensional now. So in the similar way, we will construct all the cases, and in this case, we obtained 8 elements in our optimal system. And these are inequivalent, and each element represents the class of symmetry generator. So we presented the optimal system for each case, and then corresponding to each element from the optimal system, we use the direct method to find the exact solution, which are actually the invariant solutions under optimal system. So we find the form of solutions and exact solution. So we provide the complete reductions corresponding to each symmetry under the optimal system for each case based on the values of phi of u we obtained in this case. And this is for two-dimensional case. And similarly, we presented the same study for the four-dimensional partial differential equations. So I think that's enough for today. So, yeah.
Any questions from this audience?
Thank you so much.
Why you extended the problems to higher dimensions? Is there any physical need, or you want to extend the algebra for this?
Okay, so the thing is, we don't take the value of our desire here. There is another problem. What we do, we take the equation and we take the value of our desire and we put it and we apply the method. Least metric classification for arbitrary, this is called closed form problem. We take the problem, partial differential equations, including the arbitrary value of phi of u. And then we apply the method. In the method, in the course of finding the classification, these values of functions arise naturally by applying this method. All right. So these arise naturally. For example, if you are doing the same problem for another type of equation, for example, for a KdV equation, so the value you will obtain will arise naturally. And those values may be different from this one. So this is the method which provides us this value. And the other problem is you take the value, substitute it, plug in, and you find.
Thank you, Ali.
Take one more question with one of the
okay.
It's just this one from okay, let's see what this goes.
So it's really good presentations because you are finding a solution in terms of integral equation, integral sign with the parameter in the terms of the functions.
Yeah.
So it's a good solution. So my question is, you are extend the equations with the fourth order terms.
Yeah.
You are taking two terms.
Yes.
So physically, you have mentioned that this is the dispersive term or the dissipative terms.
It's dissipation terms.
Okay.
So, you know, this has its application, which is actually if you take the particular value of phi of u, based on the value of phi of u, this equation changes meaning physical. For example, there is one value. If you plug in that value, the model becomes the nerve equations in the biomembranes. So if you take that value and that value in the biomembranes, you require higher order dissipation terms. That is important for that kind of problem. So sometimes you can, if the problem is engineering, you can add the damping term, you can add the dissipation terms according to the physical, according to the.
That's why I'm asking, because this is the physical significance if you extend the equations.
Exactly.
Thank you.
Okay, so the question from the
all NREs.
Hey.
Hi, Professor. Yeah.
May I ask a question?
Yes, please. Yes, please.
Oh, okay. So this is not question, it is actually comments. Comment is first, that very important for group classification to study equivalence transformation. So my presentation was about this one, especially, so it's much easier. Second one, that it is for optimal system of construction of optimal system. It is much easier to use Ovsyannikov's method, which is two-step algorithm, and much easier. So, and then I have idea. So, Ali, I can teach you after conference, please, and I can show you in Zoom how to do it. Especially for four-dimensional, it is very trivial. Actually, four-dimensional, it is done patir of internet. So, but I can teach you how to use Ovsyannikov's method. Thank you.
Yes.
Okay, that's why we needed you here.
Yeah.
Unfortunately.
Yes, I think you said the same thing in the last conference. Then you got busy.
No, just ask me. I will do it.
Okay, this time I will. We will do it. Sure, for sure.
Okay. Thank you, Sergey. Let's thank the speaker one.
Yeah, thank you.
Let's just go to the next speaker.
So maybe whilst I have to use
Our next speaker is a student of Kesh Governor, Kesh, Professor Moyo, are all related to Professor Peter Lee. So we have to work together. Please. So Slungile Chibase is going to speak on something slightly different from what everybody else speaks on lambda symmetries for a simple second order nonlinear equation. I think lambda symmetry is a recent development and will be quite interesting. But right now we need to connect this. You were told to wear a tie.
I didn't find my size.
Yeah.
Okay, so how do you pass?
Okay, let me first of all, we have to check here, right? Yeah.
Yes, now you can.
So the pointer is there. Page change is on the arrow.
Okay, let me see.
Just change. Okay. The pointer is the top one.
Greetings, everyone. My name is Lungile Shibase, and I'm going to be talking about lambda symmetries for a simple second order nonlinear equation. My supervisor is Prof. K.S. Govender. And I would like to thank the organizers for making it possible for me, for me to attend this workshop. So a lot has been said about symmetries, but I'll just summarize. My outline of the talk is I'll start by introducing the classical symmetry method, then move on to lambda symmetries, which is kind of the main topic for today. Then I will do one example just to show how these symmetries differ. Later on, I'll present a classification problem just before ending with some concluding remarks. So symmetries are very useful when studying differential equations, as they help us find a transformation that leaves a differential equation invariant. They were introduced by Norwegian mathematician Sophus Lie in the 19th centuries. So we use Lie symmetries to solve our differential equations. It's a tool that many people have used and it gives good results. So symmetries help us simplify equations, reduce their order by 1, or find the exact solutions. Here's how it goes. A differential equation E will admit a symmetry G if and only if the nth extension of G operating on E, taking an equation into account, is 0. What we mean when we're saying we're taking an equation into account is that we're substituting for the highest derivative from the equation. Then the nth extension of the symmetry is given by 4. In this extension here, we have eta I, which is defined recursively, and it's given by this expression where dx is the total derivative given by 6. Then the second extension of the symmetry is given by 7. So when solving this extension here, we have a linear system and one can use any computer package of their choice to find or rather calculate the symmetries. Once you have a symmetry, one of the uses is reduction of order. We use the first extension of the symmetry to reduce the order. Then in order to obtain the reduction variables, we have to solve these characteristic equations given by 9. I must have forgotten to mention that finding classical symmetry method sometimes might not work. In that case, we have to look at extensions. Many of them were introduced and they have proven to give quite good results. So here we're going to be focusing on an extension introduced by Murrell and Romero back in 2001, known as the idea of lambda symmetries. So in the standard Lie symmetry method, we look for a vector field X given by 10. Then the kth lambda prolongation is given by 11. So lambda rises in this extension here. The condition is still the same as before. What makes lambda symmetries particularly interesting is that we have the presence of the lambda term in what we call the first lambda prolongation. So in the classical symmetry method, this term is not there. meaning that there is no lambda involved. What makes these symmetries different from classical symmetries is that we have a new type of prolongation, which is lambda. We have a nonlinear system, which I will show you later on. Then there are no computer packages available, so you have to do it by hand. I know this might sound very confusing, but let me just walk you through an example. The Painley-Vaines equation that admits these two Lie point symmetries. One can use Sim on Mathematica or any other package to find these symmetries. It's a straightforward exercise. There's nothing complicated with regard to this. We're just presenting for illustrative purposes. The choice of which symmetry to use to reduce the order is determined by the Lie algebra. But due to time constraint, as mentioned by Dr. Ali, I won't be discussing any Lie algebra here. So the invariants are V equals to Y and W equals to Y prime. So after integrating and reversing the transformation, we then obtain this expression given by 15, which is of variable separable form. However, the functions involved here can be invertible. So it's so unfortunate that even after a special case of beta equals to 1/8 alpha squared, we still can't invert it. But no need to worry. There's one method that's going to help us. Let's analyze the Painley-Vaines equation, but this time we're analyzing it for lambda symmetries for the first time. We operate with the second lambda prolongation and take an equation into account. So if you look at this second lambda prolongation, we have phi multiplying lambda, we have rho multiplying lambda. There's so much nonlinearity going on there. However, in order for us to solve this, we have to make some simplifying assumptions and take rho equals to 0. But for a more detailed calculation on this Painley-Vaines equation, kindly check out our recently published paper by my supervisor and me. But no need to worry again. I'll just show you how the nonlinear system looks like on the next example. The lambda symmetry of this Painley-Vaines equation is then given by 18, where lambda is given by this. Here's the thing, when beta is equals to 1/9 alpha squared, we have a lambda symmetry. If not, then there is no lambda symmetry. So now we have an explicit solution to the Painley-Vaines equation, unlike the previous reductions with the other symmetries, where we're not able to write down y as a function of x. With that being said, let's turn our attention to a classification problem involving a second order differential equation of the form y double prime equals to f of xy. We aim to investigate, in a general sense, which equations of the form will admit lambda symmetries. As far as we know, not much work has been done on this kind of classification. So for this equation here, we operate with the second lambda prolongation and take an equation into account. Since we're trying to solve for rho, phi, and lambda that only depend on x and y, so we're going to separate by functions of derivatives of y. We have to solve the system. This is the system we solve for. It's so unfortunate that we have a nonlinear system shown by these highlighted terms here. As a result, we have to make some simplifying assumptions and take rho equals to 0, just to see what happens. Basically, we want to explore what's going to happen to this system here under a specific condition of rho equals to 0. If you look at equation 23, all those terms with rho fall away, and now you're left with phi y equals to 0. Phi now is just going to be linear in y. We then substitute into the remaining equations and then obtain phi and lambda given by 26 and 27 respectively. That's when f has the form given by 28. Therefore, the lambda symmetry of this equation is given by this first lambda prolongation 29. Let us now reduce the order of this equation using this first lambda prolongation. We have to solve these characteristic equations given by 30. The characteristics are v equals to x and w equals to 32. Then the reduced equation is dw dv equals to 33. which is a Riccati equation, and it's very difficult to solve it in general. However, according to KMK, we're able to write down an explicit solution for the Riccati equation where E is given by this expression here. And the challenge is that when we try to invert it and write it in original variables, we still have to integrate a more complicated equation. So for now, we don't have an explicit solution for this equation. And another thing is that a Riccati equation, as those of us who work with differential equation know, it can be written as a second order linear equation. And we have this linearization, and this linearization is subject to a solution of an able equation of the second kind. Therefore, we have this remarkable property that a second order equation that admits one lambda symmetry can be linearized. Let's take an equation that falls into this class. This equation demands B and D to be 0 and C to be 2a squared. Now phi and lambda given by 40. Therefore, the lambda symmetry of equation 39 is given by this first lambda prolongation. So equation 39 and 42 are both the Markov-Pini equation. However, equation 39 admits a lambda symmetry when equation 42 does not. Even if the difference is a change of sign, it's actually a complex transformation between the two. To conclude, lambda symmetries are very useful as they provide alternative reductions with the other symmetries as shown with the Paine-Lever-Innes equation. So what we've been able to do is that we use lambda symmetries to linearize equations that cannot be linearized using standard symmetries. So for future work, we're still considering a more general class of equations where F depends on derivatives of Y prime and some fewer restrictions on rho and phi. Thank you.
You sacrificed the dessert. It was such a wonderful presentation. She's all nervous. You want to take the dessert?
It was supposed to be a secret.
No secrets from me.
Next time.
Anyway. Any questions?
You had applied the least symmetry transformation method on the coordinate differential equation. Have you applied on the partial differential equation?
No, not as yet.
Are you working on it?
Pardon?
Are you working on that?
Yeah, I think towards the end of my PhD.
Yeah, it's a new idea. It would be very nice to execute.
Yeah, maybe postdoc.
Yeah.
No, I'm just saying. Please don't tell government.
Sergey, you may ask your question.
I have comment actually about equation 21. And do you know that equation 21 was classified by Lee? Later, it was also classified by Ovsyannikov.
Yeah.
Yeah, we just extended it to lambda symmetries. Yeah.
Thank you, Sergey. Any other questions?
So one comment. You were saying lambda symmetry is helping reducing the body into linear, helping it to linearizing the problem, which is very useful if you by introducing the lambda.
Not necessarily linearized, but giving you sometimes a class of solutions that might otherwise be picked up.
Yes, exactly. Because sometimes we obtain reduced OD, which is sometimes difficult to solve. Okay. It's fine. Okay. Yeah. So sometimes when we reduce, so sometimes we get more complicated equation, which is difficult to solve and difficult to linearize. So this lambda symmetry is helping us easier to
say 99%.
Oh, okay. Wonderful.
All the time.
Yes. Okay.
The whole process of calculation, just like what you did.
So
the lambda makes
yes.
not as a consequence.
Yes, exactly. Maybe you can try a non-linear OD and then you can check if it is working wonderful there or not. Yeah.
There's another comment or question from Sergey. You may ask or comment.
No, I think
Sorry,
it's
just
the
I
previous.
wanted to answer Ali. So about linearization, up to fourth order, it is done. I mean that much easier than lambda symmetry. You just apply. But after that question is, you found that equation is linearizable. Then question is how to linearize. And sometimes, and mostly, you have to solve Riccati equation, so which is not possible to find solution.
Yeah. Yes. Thank you, Professor.
I think on that note, now you can have your.
Yes. So we have a tea and coffee break now. So for the online audience, we will start again at 3 p.m. Yes, we have.
You can't say for the audience 3 p.m. The one is in Thailand. The one is
3 p.m. South African time. 3 p.m. South African time. Yes. Yes. So we have a tea break now.
So we'll reconvene at 3 p.m.
Akshay.
Yes, I am here only. Hello, can you hear me?
Yeah, actually, it's clear.
Okay,
But they did not start yet.
okay, thank you. Yeah. Can you hear me now?
Actually, I think that they did not.
No.
Maybe they are waiting for audience.
In chat, they are saying that we cannot hear you. Can you can start presenting?
Oh, really? I can hear you.
Just 1 minute. Okay, then maybe I can leave and I can join again. Just 1 minute. Okay, thank you. Okay, so just 1 minute. Yeah. So, okay, basically my talk is on shockwave interactions for ray type material model. As we know that when there is a discontinuity, two discontinuity in the initial data for a Cauchy problem, then there is a possibility of that the discontinuity happening in the system can interact each other. So basically, first, how the discontinuity comes into picture, as we know that for nonlinear scalar conservation laws, for a Burger equation like Burger equations, one can have for any smooth initial data, then they can have a finite time blow up. So after that blow up, there may be there is a discontinuity in the data that can going to propagate. So those type of solutions we are going to call it shock waves. And if the initial data, so we are taking that data to the initial point. So we are considering two discontinuity at the initial point and try to figure out under what conditions we are going to have the interactions, and after the interaction, what is going to happen. So for this this analysis, we are going to use the first method of differential constraint, which help us to construct the solutions for the system for finite time. And then we try to construct the solution for this rate type material model. This is a particular model we are considering. And then we discuss the solution of the Cauchy problem. And then we discuss the shock and rarefaction waves happening. And for a particular initial data, we just state the main results that we are going to use to say that when the shock wave interacts, then after interaction, what is going to happen. So first, the differential constant method, it says that for any strictly hyperbolic system, we can have the choices of differential constant in the form of two. which if we can append, which if we append to the system 1 under the compatibility conditions that Q has satisfied, then we can characterize these solutions along the each characteristic values. So we can solve this system along the characteristics. So here is my system. Here is my rate type material model, which is given by equation 4. And first we check that whether system is strictly hyperbolic or not. So from these eigenvalues, one can see that as each eigenvalue is different, so it is a strictly hyperbolic. And we'll see that there's a lax condition which says that whether system is whether the each eigenvalues, the corresponding fields are generally nonlinear or linearly degenerates. If generally nonlinear, then there are two types of solutions can be propagated from each characteristic field. So here one can easily see so that both the eigenfields are generally nonlinear. That means either the shock or rarefaction can happen in each eigenfields. So this based on this we can study this system. Okay, so based on the previous differential constraint for this system, the differential constraint takes the form equation 7, and the compatibility conditions for this equation 7 and the underlying systems are given by equation 8 and 9. And we try to solve these compatibility conditions. So one obvious solution, not obvious, but this is one particular solutions of this equations are given by as a constant solution 1. Similarly, we can append this second differential constraint and we can get this compatibility condition for this Q12, and we found that Q12 should be 1. And now with the help of these compatibility analysis, as I said that we can solve this system along the eigenfield. So we have written our system along the eigenfields and try to construct the solution for the Cauchy problem, basically initial value problem. So we have obtained the solution of our system in the form of equation 14 along the characteristic this with extra condition as the compatibility conditions as the differential constraint must satisfy by the initial data. So our initial condition must satisfy this equation 16. And when we are choosing this, then this also will restrict us and this will bound, there will be critical time after again that there will be a breakdown in the solution. So we construct up to that level only. So for this equation 16 will also give a critical time after which again we need to consider the discontinuity in the data and then we need to solve. So we are going to solve up to that data. So first now we'll try to construct the shock waves for our system. So for shock waves, just we'll writing the RH condition for our system and we try to solve this equation 17 to get the shock speed and the relation between the left and right state of the discontinuities with these limiting state that as we know that in the discontinuity region the left hand limit and right hand limits are going to be the UL and UR and VL and VR. So we obtain the relation between these along the shock waves, and we obtain by solving equation 17 we obtain this shock speed. Now using the lax conditions or entropy conditions, one can find that for the first shock we need to choose the negative sign, and for second shock we need to choose the positive sign. So accordingly we can get the relation between these, and this will restrict us to get the shock solutions. So basically we have obtained our shock solutions for the systems. Now to understand the rarefaction solutions, which is a basically expensive fan. So under the condition that the left state, leftmost state is the UL, that is a constant, and UR and VL and VR are the left and right states that is going to bound the rarefaction region. So we try to fill that region and construct the solutions in between those regions. So first we'll try to figure out that what is the leftmost and rightmost characteristics that in between we need to fix the states. So for that, determining those curves, we are using the left eigenvalues and the right eigenvalues that is given by equation, and that must satisfy equation 19. And solving this under these conditions, one can get and using the solutions also for the Cauchy problem, one can get the R1 and R2. Basically, these are the left and rightmost characteristics. In between, we need to fill the states. So for filling the state, we have assumed that the solution from our from our previous solutions from the Cauchy problem, and we know that in rarefaction solution, it is a continuous solution. So so we have assumed this Vxt is equals to Z e to power minus t, and this. So basically, and along these characteristics. So basically, we have assumed this solution inside the continuous solution inside the rarefaction region, which is bounded by R1 and R2, and we have already R1 and R2 in our hand. So now we need to determine this Z and zeta. So we just substitute this whatever the values we have assumed in our original system, and then it will reduce to these two equations. And with the subject to this condition that zeta must be UL when x is equals to R1, as it is obvious that the left state should left eigenvalue, it should take the value UL. If someone wants, then they can choose also zeta can be UR along the curves x equal to R2. That is the rightmost states. And one can solve this and one can get the values of zeta by solving one of the equations, and then they can fill the region of the rarefaction part. And this solution is given by equation 22 and 23. So now in our hand, we have now shock solutions and rarefaction solutions. Now we'll choose, because we have whatever we have done, it is for Cauchy problem, for initial Cauchy problem. But now we'll take the discontinuous initial data. That is basically called the Riemann problem. And this is the general Riemann problem, because here we are not taking the constant state. Here we are taking one variable as a non-constant state. So that's why we are calling this Riemann problem with non-constant initial data. Okay. So now we can using the previous solutions, we can construct the shock solutions for one shock and two shocks, where we have determined the one shock curve and the relations. This similarly, one can find for this particular initial data, one can find the rarefaction solutions. So now the main thing is that when there are possibilities of whether one shock is one wave is a shock wave, two wave is a rarefaction, one is a rarefaction, two is a shock waves. So there are different possibilities, and there may be the only case that where only one shock will come into picture, only two shock will come into picture. So all those depends on the initial data, and that those results are summarized in the form of this theorem. So this theorem says that if the initial conditions, these are the if and only if conditions. If one shock happens, then one of these three conditions must satisfy. And if this condition satisfy, then that means the pattern in the shock wave will be one shock. It contain one shock minimum, not minimum. It contain one shock if this condition satisfy. So similar, so we have obtained these conditions for one shock, two shock, and one rarefaction and two rarefaction. So now our goal that this title suggests that we try to understand the interaction of shock. So there are other possibilities of that when the initial condition is having shock and rarefaction, that is more challenging. We are still working on it. So we obtained a result up to only shock interaction. So what we have taken the discontinuity at the 0 point and x0 point, and we have stated that the initial conditions that x plus ul vl like this. So these are and these are not same. Ul and um and ur are not same. So that means there is a discontinuity at the initial point. Now, under the assumption that from the point 0 and x0, we have only one shock and one shock. So both one shock, they are going to propagate in the same directions, and they may interact. And for this particular case, they are going to interact after finite times. So after finite time, what is the pattern? What is the pattern that going to happen? So we have obtained the condition that under this condition, if the initial discontinuity is having one shock and one shock, then we'll have the interactions, and the result of that interaction will be given by one shock and two rarefaction wave. Okay, so similarly, if someone takes like from the 0 point, if the two shocks appear and the point at x0, the one shock appears, so definitely because they are having the different directions, they're going to interact after finite time. So after these interactions, what is the wave pattern after this interaction? So that is one shock and two shock. One more thing one can study, that the strength of these shock, or maybe they are going to accelerate, they are going to accelerate in their directions. So under these conditions, initial data starts from this whatever the discontinuity at 0 and x0, they will start from only one shock, only two shock and one shock, and they're going to give this accelerated one shock and two shock. Similarly, one can consider the two shock and two shock from the 0 point and x0 point, and they are for this system, they're going to interact, and after the interaction, the wave pattern is given by this R2, the rarefaction, and a shock wave. So because okay, one can say that, yeah. Anybody saying something?
Continue.
Okay, thank you.
Yes.
Okay, so okay, thank you. So one can say that because earlier I said that there are possibilities. So here, what is the achievement of our result? That it says that whenever there is an interaction, then at this level of time, again there is a discontinuous initial data. So, but the restriction of this inequality had restricted, because at that point of interaction, again we have the Riemann problem, and again there are different possibilities, but we have discarded all those possibilities, and only this wave pattern is going to happen. Okay, so similarly, so that's why this because every time we need to take all those combinations, and numerically it will be difficult. So this, in our opinion, we feel that these conditions will help us to deal with the interaction problem in the Riemann problem, in the Riemann problem or generalized Riemann problem also. Okay, so these are my results, and these are some references which I followed. Thank you.
So any questions from the audience? Yes, any questions?
There is one online.
Yes, you can ask.
Oh, because nobody asked. Actually, Akshay, I did
Yes.
not ask you before. Maybe so. What do you think if we have initial boundary conditions? For example, one boundary as a wall. What happens in this case? Like in gas dynamics, it is increasing shock wave. But what about in your case? Is it possible to consider?
Yes, but again, okay, here I am trying to solve analytically. So if someone produce the boundary at some point, like here we have taken the initial discontinuity at 0 and 2. Suppose that someone has introduced the boundary at x equal to 3. Then again, the reflective waves, the reflection and absorption we have to consider. So again, it will analytically solving, it's difficult, but I'm trying to produce some analytical results of these things. But after this interaction with the ball, then that can be studied. That can be studied, but yeah, that can be studied, but still, I don't know analytical solutions after the interactions, how, because it depends on wall, whether it's going to absorb all the, it is going to reflect all the shock conditions, or whether it can have reflect, or I can some absorption also take place now at boundary. So this depends on analytical. This will change analytical solutions drastically.
Okay. Okay. Thank you.
Akshay, I have one question. Can we solve your considered model by the least symmetric method?
Yeah. This system is already solved by Oliver. Oliver by Lee symmetry also. He has applied approximate Lee symmetry also. He has obtained the generators and tried to reduce the system to homogeneous and studied the Riemann problems. And approximately symmetries also one can apply this apply to the system, and they can get the approximate solutions to our case, our original equation.
So can we change the boundary conditions accordingly?
So in this case, the boundary condition, it's applying, it's very difficult, because I said now, absorption and reflection, these type of things will come into picture. So again, this will be difficult. And my problem is only initial value problem. So there's no problem. But if someone puts boundary condition, yeah, my case is discontinuous initial data, the Riemann problem, basically generalized Riemann problem.
Thank you, Akshay. Any other questions? Okay, thank you so much, Akshay.
Thank you.
Okay, so the next candidate is the Mohammed Tanavi. Approximation solution of the geomagnetic dynamical system, extended center manifold, and the criteria for the synchronization. So are you there, Mohammed Tanavi?
Mohammed, your microphone is off.
Mohammed Tanavi, are you there?
He is there, but microphone is off.
Yes, let me just send him a message in this chat box.
He's there?
Yeah, he's not here.
Maybe he is reconnected.
Maybe it's reconnect.
That's it. Last speaker is not working. But what did he's not online. And he had to respond to you. Yes. Thank you. Okay, we can conclude day one and then.
So today we conclude the today's days.
Tomorrow we will start at
So tomorrow we will start at 9 o'clock morning, South African time. Yeah. So first day is very wonderful for all of us. I thought we are learned. Yeah.
Oh, yeah. I thought you.
Mohammed, you unmute yourself.
Can you please unmute yourself?
Unmute yourself.
Unmute.
Yes, you can present your.
I
Yes,
can
you can.
present now. Yes, yeah.
Yes, yes. You just press the Control L for the full
Okay.
screen.
Full screen.
Control L. Press Control L.
Yes. First, thank you for present my presentation, my work. Thank you for Dr. Moya, Ali, and the organization. It's a pleasure to speak about my work. Title: Approximate Solution for Geometric Dynamical System, Extended Center Manifold, and the Accreditation for Synchronization. It's in my work with collaboration with Professor Hamdi Abdelgawad and Basma Abdelaziz. It's outlines of my work. I speak about mathematical formulation of dynamical system, approximate solutions, complex geometry, dynamical system, synchronization also of complex geometrical dynamical system, and the extended center manifold around the equilibrium point. First, mathematical formulation. Speak about chaotical phenomena have experimentally verified across science and engineering. Many previous study of nonlinear dynamical system close to get numerical techniques or analysis of phase portrait and bifurcation of dynamical system. Also in this work, we find approximate solution for nonlinear geometric dynamical system by construction, Picard iteration, conversation theorem, creation of synchronization of complex and techniques for extended center manifold around the equilibrium point. Dynamical system describes a turbulence geometric field was introduced in reference 5. This is equation wise 5. One describe nonlinear geometrical dynamical system, which U naught, V naught, W naught is the initial condition. Can take also this transformation to simplify the dynamical system 1 to equation 2. Also, it must be clear to evaluate diversion of equation 2 for dynamical system. It must be less than 0. First, we can write equation 2 as a matrix M U dot V dot W dot as M U V two participant matrix of linear coefficient multiplication U V W and nonlinear. So I divide equation 2 to part of linear and nonlinear term, which M is coefficient of linear term. In equation 2, so we can write the equation 2 as U as a vector, U V W equal A. We take this transformation exponential MT U capital, which is U capital, V capital, W capital, with the same initial condition for U small, U V W. Also, by derivative equation 5, we can given this derivative equation 5 to U dot two parts MT U dot plus MU, which U dot is a vector derivative and U capital dot also a vector derivative. From equation 4 into equation 6, also we can describe relation between E exponential MT U capital dot as equal nonlinear term of equation 2, or we can write E M2 as a vector as description of U dot V dot as nonlinear term of equation 2. And this, if we can to integrate equation 7 to find U capital, V capital, W capital, and its discretization or generalized formula to N formula of solution. NT U0 is the initial condition, is integration of exponential minus T, one multiplication of nonlinear terms of equation 2 with the same initial condition of equation of system 2. at n equal 1 can given first approximation, at n equal 2 equation 10, as n equal 2 can find the second approximation. It's like iteration to find the approximate first and the second, also can third approximate solution to close exact solution of dynamical system 2. If we apply equation 9 or iteration 9 to dynamical system 2, first we get zero approximation given for linear term of system 2 only. We take roots equal m plus minus minus gamma square to gamma mu, equation 14. It's driven to given periodic solution for zero approximation, and use also the iteration of 9 using the zero approximation to find the first approximation of system 2 u1 v1 w1 is equation 15, 16, 17. And we also calculate at various time t equal 1, t equal 2, the zero approximation, and the first approximation to calculate absolute error between zero approximation and the first approximation. The result of equation 15, 16, 17, which is classification of the first approximation, display figure 1 IV. This is a chaotic behavior of solution, V1 against U1, W1 against U1, also W1 against V1, and this figure IV is three dimension for phase portrait of U, V, W is shows a chaotic behavior of equation 2 of geometrical dynamical system. Here we extended the dimension of dynamical system 2 by using U1 as 2 parts of system or 6 dimension, with take the transformation U1 plus I2 V1 IV2 W1 I2 is to extended to drive to get 2 dynamical system at the real part and the imaginary part. So equation 19 and 20 is called 6 dimension or extended dimension of complex dynamical system. Here we use equation 19 and 20 as real and imaginary to study or to choose synchronization of 2 systems. Synchronization phenomena of chaotic dynamical system have recent match at 10th century. Chaotic dynamical system is to show or create a pair of some relation between function or between factor of 2 process of interaction over time of 2 dynamical system, especially in mathematical ecological dynamical system. Aim is to control a magic chaotic population, to know predict of population habits depend in 2 dynamical system, depend in the system to interaction of another system. So this phenomena give the understanding of how to apply chaotic ecological system to predict the population of computing species in or one habits using information about similar population in another system, factor of another system. Here we speak about or we get criteria of for synchronization of real and the imaginary part of equation 20 and 19 and 20 of real and the imaginary part. Under we take a condition of imaginary and real if they're linear independent. So we write linear independent between component of real and imaginary part. So use equation 21 as a condition for real and the relation between component real and the imaginary part to driven equation 22 and 23 is dynamical two dynamical system with some condition of 24 of parameter P1, P2, also P3, and solution of solution of equation 22 real part and imaginary part are given by the same way in part 2 by Baker iteration. So it's first iteration of first approximate solution of real part and is the same of imaginary part, as here in this case are equal for synchronization of dynamical system of real part and dynamical system of imaginary part. Here we get extended center manifold. Extended center manifold like surface around or neighborhood of equilibrium point. So equation 2 we can rewrite as this formula. U dot function f u v w f2 also w dot, we can rewrite or write equation 2 as a function of non-linear and linear term f1, f2, f3. We assume at B is equilibrium point 0, 0 system. So we find like surface around the neighborhood equilibrium point 0, 0, 0. So U VW can write this formula. This is equilibrium point, and M is a matrix of eigenvector related equilibrium point 0, 0, 0, and new component U1, U2, U3, where M is a function as the value of matrix of eigenvector. So I can write M U V W as a previous component with new component, or new component with previous component. Now we can also derivative equation 27 U dot V dot equal M U first new component with the same value of equation 2 F1, F2, F3. Also we can write a new component with previous component M inverse matrix U dot V dot W dot, and where the value F1, F2, F3 is right hand side of dynamical system 2. Also we can find from this relation, can get by know U dot V dot W dot, we can find F capital 1, F capital 2, F capital 3. So it's easy to find from equation 27 to 29, 27 to 29 to find a new component U1 dot V U dot U3 dot is new dynamical system for new component U1, U2, U3. Take also the consideration, or we write the transformation, a relation between U2 between new component each other, like depend on U1, U2 as a function of U1, U3 as a function of U1 to express U2, U3 as a function of only U1 to come find U dot only depend on U1 with some condition for a new factor beta 3, beta 1, beta 2, rho 3, rho 1 is the equation 34. This is a condition, and the relation between new component each other depend on U1 to express only U1 dot as a function of U1, and by solving this equation by integration, we can find U1 depend only on the coefficient of parameter of dynamical system 2. And solution of equation is 35 displays a figure for 3-dimension and test plot for U1 against parameter dependent parameter of dynamical system 2 against new Also, the shape of surface closed or surround equilibrium point against the gamma and the next plot. Also, figure V is center manifold, extending center manifold of U1 depend against T alpha and the next plot near or closed equilibrium point 0, 0, 0. For some conditions of alpha gamma also constant of integration, it's a free parameter. We take this value to show the extended center manifold around 0, 0, 0. This reference. Thank you.
Yes, any question from the audience? Any questions? Yes, I have one question. Mohammed, why you are choosing the center manifold theorem? Before we are studying the dynamical system, first the stable manifold theorem and the second is the Hartman-Gromman theorem. So why are you choosing the center manifold theorem for solving this system?
Center manifold not using to solve the system. Center manifold here to show like a surface near equilibrium point depend in a new component given U1 new component of dynamical system U1 dot U2 dot U3 dot to find U1 is neighborhood or like near or surround or closed equilibrium point 0, 0, 0, like a surface near equilibrium point 0, 0 by new component uses for
Mohammed, actually
yes.
Stable manifold.
Just one thing from my side before I hand to Prof. Tole, don't forget to scan your QR codes on your way out. We will do 2 more prize draws at the end of the lecture. Maybe
Okay, thank you so much, Mohammed. So we conclude. So tomorrow we will resume at sharp 9 o'clock. So thank you so much.
Okay. Okay.
So let's talk about the last session.
I think you should go there.
So let's start for that. And I mentioned 2 days ago the future starting.